Guys, welcome and hello. I appreciate you coming down on a quiet weekend on campus to do a little study session with me. Um, I'm going to spend 2 to 3 hours. If you need to leave early, if you need to watch the video of some of it later, you can certainly do that. There's no pressure here. I'm not going to be rushing. I have no agenda. I'm going to try my best to give you a variety of problems that are related to these chapters, and that would be like similar to exam problems for us to work on together. We'll talk it through, but you guys should definitely ask questions because there's no real time constraint now. We have all the time in the world. I want everybody to leave here feeling at least maybe not like you're perfectly ready for the exam, but at least I want you to leave here feeling like you know what you want to work on for the next whatever it is, a few days leading up to our exam. So hopefully by being here today, you have a nice head start on getting kind of on top of all of the material. Um, I kind of have it broken down according to the 3 chapters. Chapter 4 by far is the longest part. We had a lot of things to talk about there, and you're going to see in the review today, I'm going to be doing lots of problems about Chapter 4. This is basically the whole vector space theory. So you're talking about things like subspaces, basis and dimension, that involves like spanning sets and linear independence and stuff like that. And then we look at those concepts for specific cases like null space and row space and column space of a matrix. And so there's a wide reach to the stuff from chapter 4 for sure. Then chapter 5, this was a much shorter section, but it's still very important. You definitely want to be solid on it before Thursday. Chapter 5 is about inner product spaces. You will want to know the axioms of an inner product very, very well, as well as just the basic concepts of, angles and norms and using the Gram-Schmidt process to orthogonalize a set of vectors, some of that kind of stuff. So for sure, chapter 5, you're going to see quite a bit of questions about that one as well. And then we come to the wild card, which is chapter 6. I don't know how many of you have already tried to take a look at this one section. We're going to spend Tuesday totally going over it, but I'm actually going to try even today to do some of the chapter 6 problems so that you have a head start on it. There is homework to do for this 6.1 for Tuesday, but as I mentioned last week, I'm going to be doing it basically in class with you. So you can take it or leave it if you want to work on it ahead of time, as fine. Some people don't like to feel the pressure to learn everything in the last 2 days before the exam. So if that's sort of how you feel, then I would definitely recommend getting a earlier start on reviewing that as well. So by the way, it's good to see all of you guys here. I'm glad that you could make it today. And I'm really going to just jump into some problems now. I'm not going to do a big crash course overview of all of this stuff again. Remember that I have all of our lectures in Canvas. So if there was a particular section, and I've even labeled for each class day, what topic were we talking about on that day. So if you need to just go back and sort of hear it from scratch again, you can do that. But I think what I would like to do is sort of just bombard you with some problems, some questions, and I'm going to get these questions from 2 different places. One place is from the review session handout, which is in Canvas. So it's in our Canvas page. I'm going to do some of these. And then I also printed out another sample midterm from a different year. You already have 2 sample midterms in Canvas. This is like a 3rd one now. So just to create even more problems. And I may not do all of these problems today. If I feel like we've covered everything and people are getting a little tired, we'll just let it go. But I'm going to try to jump around and make sure that I talk about everything. Does that sound like a good game plan? Yes. Okay, fantastic. Then let's start with practice problem number 1. And here's what I would like to do, guys. I would like to find a basis. Sounds like a standard type of topic. Find a basis for the null space of the matrix, and here I'm going to give you a matrix, 1, 2, 0, -2, 3, and then the second vector is going to be -4, -8, 0, 8, and -12. So that's a standard problem. It involves the null space of a matrix. Remember, there's a handout, sort of a little chart that talks about null space, row space, and column space, and how to find a basis for all of those things. So this would be kind of a standard problem in that topic. Okay, so does anybody remember what we would need to do for finding a basis for this null space? Sorry? Solve the matrix, meaning?
Get into row echelon form.
Okay, yeah, we need to do EROs on this matrix. And I'll also just remind you, here, I'll start the solution right here. I'll also remind you that when we are doing this process, we should imagine augmenting the matrix with zeros. So for the null space, you always augment your matrix with a column of zeros. And when I do these EROs, take a look here, guys. The first row doesn't change at all. But if I take 4 times the first row and add it to the second row, I can get the second row to actually zero out. It completely zeroes out because the second row is actually just a multiple of the first row. So I tried to start off with one that's pretty easy. So this is just, A1, 2 of 4. I'm not going to be as fussy about the ERO notations on this exam, but it always helps to, be careful with this stuff. If you make a mistake on the EROs, but you still answer the question correctly based on what you got, I'm going to give you a lot of partial credit for that. But otherwise, you definitely can count on partial credit for partial progress on these kind of problems. So here you're looking at this null space, and you're going to be solving for these constants. So Yair, once I get my row echelon form, what should I do next? Since this was your idea.
Solve for each line. Yes, 3 variables.
Solve for these constants, exactly. And by the way, how many free variables do I have here? I have 4 of them, right? Which are actually C2, C3, C4, and C5. Normally, I relabel those as like R, S, T, and whatever. I think I'll just leave them as C2 through C5 in this case because there's so many of them. And I just really need to solve for C1 in terms of the other constants. So let me write down that first equation. C1 plus 2C2 minus 2C4 plus 3C5, that all should add up to 0. Okay, and so if I solve for C1, I'm just going to move everything to the other side of the equation. So -2C2 plus 2C4 minus 3C5. And now I'm going to write down my null space. Okay, so I'm not ready to talk about the basis for it yet, but I just want to write down what is the null space. So the null space of A is the set of, by the way, remember that the null space is always a subspace. I'll just add this here, guys. It's a subspace of Rn, and in this example, the n is 5, because there's 5 columns in the matrix. So it's a subspace of R5, which tells me that I should write down 5 slots to this null space vector, right? So far, so good? Again, for those of you who just came in, I'm not on any agenda here. Like, you can ask a million questions. We can go slow. If there's questions, don't hesitate to ask. We're just doing a standard problem, but every problem's a little bit different, so you might have a question. But this is a subspace of R5, and there's 5 slots that I need to write down. For the C1 slot, I have -2C2 plus 2C4 minus 3C5, right? That's the first entry, and then comma, and the second entry would be C2, the third entry would be C3, and then C4, and then C5. And this would just be such that, and then we just have to point out that C2, C3, C4, and C5, those are real numbers. Okay, so that's what the null space is. So how am I going to get a basis for it?
Bust out the variables.
Bust out those variables. That's it. That's exactly right. Remember, there's sort of a three-step process. The first step is write down the form of the vectors. That's what we've done so far. After that, we have to bust out the variables. And then after that, we have to make a list of our basis vectors. So what I'm going to do here, guys, is I'm just going to rewrite this with my variables busted out. So this is going to be, I'll bust out the C2. When I bust out C2, I get a -2, and then a 1, and then a 0, and a 0, and a 0. So C2 times that vector there. And then the next one is C3, which is multiplied by, there's no C3 in the first slot, there's no C3 in the second slot, 1 C3 in the third slot, nothing, and then nothing, like so. Whoops, that should be a plus. Plus, and then C4. And I go across my vector and I look, where do I see the C4? I've got 2 of them right here in the first slot, none in the second slot, none in the third slot, 1 in the fourth slot, and none in the fifth slot. Okay? And then I do the same thing one more time, which is for C5, right? In the first slot, there's a -3 right here, right? And then nothing, and then nothing, and then nothing, and then there is a C5 in the very last slot. I'm literally just doing algebra here. This is the busting out the variables part. C2, C3, C4, C5, those are just real numbers. Okie dokie. So that's my busted out expression. So bust out the variables. If you write BOTV, I'll know what you mean. Okay, so that's busting out the variables. And then we have to make our list for our basis, and the basis is therefore, it's just literally the vectors that are left behind. So you just ignore the constants. Remember, when you're writing out this basis, guys, you should not have any letters in it. It should just be specific vectors that are listed here. So the first vector, and then the second vector, 0, and then the third vector, and then the fourth vector, like so. And that would be your basis for the null space. Okay, so kind of a standard process here. What do you guys think? Is it all clear? If I asked you to check that these vectors were really linearly independent, would you know how to do that? Levi?
Just make sure you're not scaling multiple.
That's only when there's 2 vectors. So I have 4 vectors here, so I can't just look at scalar multiples.
Make sure you're not scalar combinations.
Right. Make sure that no vector is a linear combination of the others. But how do you check it, like in practice? How are you going to do that?
Would you just take the dot product?
No, this is before we get to inner product spaces. Put it in a matrix. How do you put it in a matrix? You got it. So put those vectors vertically into the columns of a matrix. Let's just do it, guys. Let's just make sure everybody knows how to do this. If I asked you to check that they are Li, then the way you would do that is you would lay these vectors vertically into the columns. The first vector goes there. The second vector goes in the second column. The third vector into the third column. And the fourth vector into the fourth column, right? Like so. We still augment this with all zeros. For the Li check, we would augment it with all zeros. You can probably tell that if you were to permute the top, well, maybe I'll just do it. If you were to move these rows around by doing permutations, I could move the second row to the top and the third row to the second row and the fourth row to the third row and the fifth row to the fourth row. And then the top row would go down here. And obviously, I'm going to zero out the bottom row by using multiples of the upper rows. But the key thing is, even without doing any more EROs, you can see here that this matrix has no free variables. And if you remember, no free variables, let's just write that down. That means Li, right? no free variables implies that these vectors are Li. Please.
From there, once you have the zero out vector in the bottom, you wouldn't include that in your solution, right?
I mean, you can just write down a row of zeros, but it doesn't mean anything. It's not really pertinent to your conclusions, right? The conclusions always are surrounding the columns and the pivots. And in this case, every column has a pivot on the left side of that bar. So yeah, this would be a conclusion of no free variables, and so they are Li. Now, if I don't ask you to check the Li and you just wrote this down as a basis according to how the question was phrased, that would be good enough. I was just reminding you how to check if a set of vectors is Li by using a matrix, and this is it. Notice, by the way, that there's a lot of cases where you get a matrix that is not a square size. So don't be thinking of the determinant as the end-all be-all of this topic, right? Because if the matrix is not a square size, you cannot use a determinant, and you'd be forced to do EROs on it. Okay? So what is the dimension of my null space then?
Would it be 5?
Yeah, it's 4 because it's just the number of vectors in this basis, so it's only 4. It's a subspace of R5, but it's only 4-dimensional. And what is another word for the dimension of the null space? It's also called the nullity, exactly. So the nullity of A, for this problem, the nullity of A would have been 4. Okay, and by the way, that's compatible with the rank of A. Can somebody tell me what is the rank of this matrix here?
1.
One pivot, so it's a 1, right? And so hopefully everybody's kind of got that rank nullity theorem in mind. If I add the rank to the nullity, it's supposed to add up to the number of columns in this matrix. And in this case, you can clearly see 5 columns there. Yeah. Okay.
But the dimension of the null space is 4, but like the actual dimension of the matrix C is 5, right?
Okay, we aren't living in a world of matrices here. We are living in this universe right now.
I guess in that universe, it's a dimension of 5, right?
R5 is 5-dimensional, and this null space is what I would call it is it's a 4-dimensional subspace of R5. That's a fair way to say it. Absolutely. Yeah. Let's do a quick any other questions first?
I was just gonna say, like,
Please.
if let's say you're given a matrix and the dimension is 6, and you
Stop. You're given a matrix and its dimension is 6. Does not make sense to me. A matrix doesn't have a dimension, right? A vector space or a subspace has a dimension. This matrix is a 2x5 matrix whose null space is a subspace of R5, right? But the matrix itself, I get that a lot, so I just wanted to pick on that immediately. There is no such thing as a dimension of a matrix, right? A matrix does not have a dimension. It has rows and columns, m value and an n value, but the matrix itself doesn't have dimensions. So I didn't mean to cut you off, but that's a point of a confusion for a lot of people. I had to
just for column number 3, it has all these vectors.
So that's a whole bunch of matrices. That's not one matrix, that's 6 matrices in this universe of M2x3.
Okay. Because I was gonna say, because when you lay down all those into one big matrix,
yeah,
you're gonna say that n is 6, right? Or k is 6?
Yeah, the k is 6 because there's 6 vectors there, and in that case, the dimension of the vector space is also 6. But it's not the dimension of the matrix, it's the dimension of the vector space, which is the M2x3 of R in that example.
The reason I was saying that is because I wanted to follow up by saying, if your dimension of the vector space is 6 and you have 6 pivots, then you should know that it is linear independent, right?
Yeah, that's true. You'd have no free variables because you'd have a 6x6 with 6 pivots. Yeah, that's a invertible matrix for sure.
I just want to like understand the vocabulary, you know. So
There's a lot of terminology. There's no question about it. Yeah. Good question. Let me ask a follow-up here, guys, while we're at it. For a follow-up, find an orthonormal basis for the row space of A and the column space of A. So far we were working on the null space of A. That's what's in blue here. The blue writing is all about the null space of A. And now I want to work on the row space and the column space. So first question is, how do you find the row space of a matrix? Let's start with the row space. How do you get the row space of the matrix? Anybody remember?
the way you find the row space, is it the same kind of like how you find the col space?
Yeah, they're very similar. They're very similar, but can I get somebody to tell me precisely, how do I get the basis for a row space of a matrix?
The pivoted rows.
Just take the pivoted rows. Exactly. So here's your, we don't even have to do any more work. We already have the work here. This is our row echelon form. So we take that row echelon form, guys, and we just grab the pivoted rows. By the way, the dimension of the row space, if you remember from the handout, it's just the rank. And same thing for the column space. There's a lot of similarities. The row space and the column space are both one-dimensional on this problem. Right, so the row space, let's just say basis 4, and go straight to the basis. The basis for the row space is just the pivoted row that we've written down over there. 1, 2, 0, -2, and 3. It's only one-dimensional. And so I only have one vector in that row space. Yeah, does that make sense? So I have a one-dimensional row space, and I just grab the pivoted row, piece of cake. Now, it's asking us for an orthonormal basis for the row space. So remember that for an orthonormal set, you have to have, first of all, you have to have vectors that are orthogonal to each other. And secondly, you have to normalize those vectors so that they are unit vectors. So my first question is there anything to orthogonalize here? Actually kind of a trick question. Guys, when there's only one vector in your set, we only have, this is only one vector, right? Then there's nothing to sort of make it perpendicular with, right? You would have to have 2 or more vectors. And if there were 2 or more vectors, we would need to orthogonalize them by using what procedure? The Gram-Schmidt process that you just did on the homework this past week, right? So normally we would have to use the Gram-Schmidt process right now to orthogonalize our basis. But since the basis only has one vector in it to begin with, there's nothing to orthogonalize. So we can jump straight to the normalization phase. Once the vector, so remember my diagram in class last week? I said, here's a basis for your vector space. And then in the middle of the board, I had orthogonal basis for the vector space using the W's. And then on the right side of the board, I had orthonormal basis for the vector space after you normalize the vectors. So it's always that process. Find a basis, then orthogonalize it, and then normalize it. Right? If I'm asking you for orthonormal. If I don't ask you for an orthonormal basis, well, then you don't have to normalize anything, because that's not what's being asked. But here I'm asking for that. So what you have to do is normalize this basis vector. This is what I last week would have been calling V1, which is the same thing as W1 in the notation of the Gram-Schmidt process. This is literally just your W1, and now the only thing left to do is normalize it into what I called U1. Okay, so my orthonormal basis, we can go straight to it. My orthonormal basis would just be this vector. Remember how we do it? We take this vector and we divide by its norm. Now, to find the norm of a vector, Okay, so just to remind you guys again, the norm of a vector is the square root of the inner product of a vector with itself. Now that requires you to have an inner product for this formula to make any sense. So I have to ask myself, what is the inner product that I'm supposed to use here? Standard inner product, because they didn't give you any other inner product to use, and you're working in this universe. In the universe of R5, you can see 5 slots in that vector. In the universe of R5, the inner product that you default to, if nothing else is given to you, you would just use the standard inner product. So you're just going to take this vector that we've already calculated, and we're just going to divide by its norm, which is the square root of 18. Is it 18? 1 squared plus 2 squared plus 0 squared plus 2 squared plus 3 squared, right? So you just add all that up. So that's 1 plus 4 plus 4 plus 9, which is 18. So you could just throw a square root of 18 on the bottom of that, and that would be fine. You can put that as a final answer. It's not necessary if you want to. Some people like to just look at it this way. You can put that radical 18 under every single slot. I don't mind, but you don't have to do this if you don't need to or don't want to. You can just leave your answer in either one of these forms would be okay. The other thing you don't have to do is you don't have to simplify the square root of 18. You might think, oh, well, I can pull out a 9 and simplify that radical. I don't need you to do that. You can just leave radical 18. In fact, I prefer it. I prefer if you leave your answer like that, because then I can see easily that you knew how to calculate it. Okay, is everybody good with this orthonormal basis for the row space? Great, let's talk about the column space. Same question for the column space. First thing is I need to get a basis for the column space. I have to find a basis for the column space of A. And anybody remind me how to do that?
Pivoted columns.
The pivoted columns of what? Yeah, not this pivoted column, which would be 1, 0. You have to go back. You don't have to do this with the row space, but for the column space, you have to go back to the corresponding column in the original matrix. So that would be 1 and -4 in this case. Yeah.
You said for the row space you don't have to, but is it something you can do?
It is okay to do that too. Yeah, if you want. Now in this case, you go back to the original row. It's literally the same thing. So that's actually optional for the row space. But for the column space, you must go back to the original columns from the original matrix, which in this case would just give you this column right here. Remember that the column space is a subspace of Rm. And for this matrix, as you can see here, this matrix has 2 rows. So the Rm would just be R2 in this case. So there's your basis for the column space. It's one-dimensional, which is exactly the same dimension as the row space. And the only thing left to do is to orthonormalize it. Again, you don't have to use the Gram-Schmidt process when you only have one vector. You don't have to use the Gram-Schmidt process. So all you have to do here, guys, is come up with your orthonormal basis by normalizing this vector. And that just means you have to divide by the norm. The norm of this vector would be what?
17.
The square root of 17. So I would probably write that as 1 over radical 17 and -4 over radical 17. And that would be a good answer. That would be a good answer. Okay, does this make any sense? So this problem is already reviewing a lot of stuff. It's reviewing row space, null space, column space. We didn't actually have to do the Gram-Schmidt process here, but at least we kind of have in mind this whole procedure of taking a basis and orthogonalizing it and then normalizing it to get the orthonormal basis. There's quite a bit of content just in this one problem. Okay, questions, comments, complaints? Anything at all?
When you perform the 0 check for the very first question.
Okay, what are you talking about?
Oh, my apologies. For the second midterm sample.
Okay, I don't have that in front of me, so that's a different topic completely. So before I take that question, Is everybody good on what we've done here? Okay, so you're asking about a zero vector check. So
Yeah.
I'll take that question now and then I'm gonna do an actual example based on that.
Okay.
So what's the question?
I just wanted to confirm that when you have a polynomial and you're performing the zero check, you're gonna plug in the zero every time for what? I'm just confused at whether you plug it in for the regular variable or for the other one. I mean,
You're always plugging it in for the coefficients, if that's what
Okay.
you're asking about,
Yeah.
not for the x in the polynomial.
Okay.
Yeah, it's always gonna be for the coefficients, yeah.
Before we move on.
Yeah.
For this follow-up.
Yeah, sure.
When they're asking for like orthonormal or anything or orthogonal, related.
Mhm.
Would you always want to refer back to the original, given like matrices?
I think it's hard to make that statement because you don't always have a matrix in every problem. I could be giving you a bunch of polynomials, or it could be a bunch of functions. It could be in a different universe. So orthogonal and orthonormal, those concepts are not, attached specifically to matrices. It could be anything. It could be these various different universes that we've learned about. It could be any of those. So I wouldn't maybe hardwire any direct connection there. Yeah. Kim?
For the basis for state A, why you will use like the first one, but not the entire thing?
It's because, and unfortunately I erased the matrix, but all of those other columns are just multiples of the first column. And so they would just be redundant and they would be creating linear dependencies. Remember that once you've done the EROs on the matrix, those pivoted columns are the only ones that matter. Any other columns that are unpivoted are going to be the ones that create linear dependencies and free variables, which we don't want. And so we clear all of that out. Yeah. Okay, great. Good question. Let's do another problem. Let me come back over here. Speaking of polynomials, why don't we do this example here? I'm going to do number 2.
Which one are you going based on?
I'm going off of just the review session, handout that's in Canvas already. I'm just kind of going through these problems. So I'm going to create a set S, but I'm also modifying the questions a little bit to make sure that I'm covering as much as I can. So I'm going to make a set of polynomials, 2 minus x squared, 1 plus x squared, and 3 minus x. And then I'm going to ask to decide if S is a spanning set for P2 of R, Li, both, or neither. Yeah, so let's try that. I like these kind of problems. You'll see them in both of the sample midterms that I've posted in Canvas. I give you a set of vectors, and I ask you this 4-part multiple choice question. Okay? Yes, Oscar.
Would you put this into a matrix?
I would in a minute. Let's do that for sure. Before I do that, it might be helpful. Remember, guys, when you have this 4-part option, 2 of the answers can be immediately removed. Do you remember this? We even did, I think, a group work on this. If you simply look at how many vectors you are given, as well as the dimension of your vector space. So you can see that the vector space here is P2 of R. What is the dimension of that? 3, right? And then how many vectors did they give us? 3. So when those match, when these 2 numbers match, then you know that it cannot be only a spanning set and it cannot be only Li. It's going to either be both or neither. And now's where what Oscar was saying is exactly the right thing, which is that we could put these vectors into a matrix. You should put them into the columns of a matrix, just like we always do. So the first vector, 2 minus x squared, I would probably write it out like that. A 2 for the constant term, there's no x term, and then there's a -1 on the x squared term. And then for the second column, I would just have a 1, a 1, and a 1. And then the third column would have a 3, and then a -1, and then a 0, because there's no x squared on that. And normally we would be augmenting, you saw me do this a lot, with either zeros or number symbols. Remember that the zeros are what tests for Li, and the number symbols are what tests for whether you have a spanning set or not. However, because this is a square matrix, and because you've already ruled out the 2 wrong answers, we can decide whether these are both or neither just from this matrix. What do you think I'm going to do with the matrix? Take the determinant of it. Anytime it's a square matrix, the determinant is going to be a great tool to use. So if we take the determinant of this, we can get our answer pretty easily. I'm just going to use the arrow method. So the first diagonal gives me a 0. The next diagonal gives me a 1. The next diagonal gives me a 0. And then I have to subtract the diagonals going the other way. This is just the arrow method, which we do still need to know. Then we subtract -2, and then we subtract 0. You can see that I did that all in my head. That's because I've been doing this for a long time. If it helps you to recopy the first 2 columns and actually draw your arrows on it, that's fine. You draw these diagonals like so, that going this way like so, and that's perfectly okay. But the point is that this determinant is not adding up to 0, right? It's not adding up to 0. And what do you conclude for the answer based on having a non-zero value for the determinant? Levi? Well, then it is both. It's either both or neither, right? We already crossed off the other 2. So it's either both or neither. And this is a good thing, guys. Remember that good goes with good. So if the determinant is not 0, that's a good thing. And having both as an answer is also a good thing. It means that this is a basis for P2 of R, because it's a spanning set and Li. Make sense?
I was just gonna ask, like, if you didn't take the determinant,
Mhm.
and you just found your pivots.
Yeah, you could also just do that. You could, do some EROs here. That would be no problem. So the bottom row, I'd probably put it up on the top, and then I'd leave the middle row where it is, and then I'd move the top row to the bottom. And then if I did one more step, doing this kind of sloppy, you don't really have to be getting these pivots to be perfectly equal to 1s. But what you'll notice if you do these EROs, so 2 times the first row added to the bottom row, we put a 0 there, a 3 there, and a 3 there, and then a 0/number symbol. And then I have to do another step to turn this into a 0 and a 1. But you would get pivots going all the way down the main diagonal, and that means no free variables and no pivot in the far right column. And that would be good enough to conclude that it's both. Kim?
If the determinant is equal to 0, there will be neither.
That's right. If the determinant had turned out to be 0, the answer would have been neither in that case.
So if
Yeah.
it is neither, there is nothing, or
It means nothing. It means they're not a spanning set. It means they're not Li. We spent too much money and we didn't even manage to get a basis for it. Yeah, that's exactly right. Yeah. So that makes sense, guys.
Yeah. Can you I don't know if you could briefly explain. I remember one of the lectures you were talking about of a matrix is, I guess, short and
Oh,
I'm gonna say fat.
the shape of it.
Yeah.
Yeah. So this one is totally perfectly square. So when it's a totally perfectly square matrix, it's either going to end up giving you a both or a neither, depending on this determinant. Yeah. If the matrix is tall and skinny, then it has no chance of being a spanning set, right? And if it's wide and spread out, it has no chance of being Li. So in those cases, then you would be crossing off, so like if it was tall and skinny, you'd cross off this one and both. And then you would still have to test for Li.
On the skin.
Yeah. And if it was wide and spread out, you would cross off Li and both. And you'd still have to test whether it was a spanning set or not.
So then would you say that both is a little sensitive to the shape of the matrices?
Oh, for sure, for sure. And it's hard for it to be both, right? That's like the hardest outcome. Remember, I drew that little chart where I showed that in every problem, neither is always on the table, right? That's always one of the two options that you cannot eliminate quickly. So it's neither or one of these other three, depending on whether it's tall and skinny or wide spread out or perfect square. Exactly. Okay, let's try, maybe we should try, I'm getting some good questions on this. Why don't we try another one that's similar to that? This time I'm gonna actually go to another old exam. So there's already 2 sample midterms in Canvas, but I've got plenty more I can go to. So let's do another problem that's kind of like that one. And see what you think about this one. This is number 3. My vector space V is going to be the set of P of X in P3 of R this time, such that P prime of 3 is equal to 0. I'm going to take that vector space, and then I'm going to take S to be the set of 1, and then 27x minus x cubed, and then 6x minus x squared, and then 2 minus 3x minus 4x squared plus x cubed. And I'm going to ask exactly the same question. Decide if S spans V, Li, both, or neither. Same question as before. Yeah, okay. Yeah.
I don't know if you can base like an initial thought process because of the 1, or is that because what I would answer is probably be not linear independent nor a spanning set, or well, the dimension is 4.
The dimension of what?
The S, right?
Okay, S doesn't have a dimension. S is just a set of vectors. So
The dimension of P, sorry.
in this case, the dimension that we would be talking about is
Yeah.
for V.
Yeah, I was basing it off that.
Do we know what the dimension of V is here? I know you want to say it's 4 because you see the P3 of R there, but it's not 4. Because my vector space V is not equal to P3 of R, but rather V is only the part of P3 of R that satisfies this condition. It's tricky, right? If this problem had said V equals P3 of R, then yeah, so like on this one was easier. This one was easier because the V was just P2 of R. No problem. It's 3-dimensional and there's 3 things in S, so this was perfect. But over here, my vector space is not P3 of R. My vector space is this subspace of P3 of R of those polynomials such that when you plug in 3 into the derivative, you get 0. So for example, if I was to write down, actually, let's try and find as a extra step here, I'm going to try to find a basis for V.
Professor, how were you done that before?
What's that?
Have you ever?
I have done a problem just like this in your lecture notes. If you go back, the only thing was the one that was in the lecture.
Oh, it was a 5.
P of 5 equals 0.
I did.
So you've seen one of these before if you've been in class, that I did one almost exactly like that. So here I'm just giving a slightly different condition to something that we have definitely done before. Yes?
What's the P? What's that?
V?
No, the P3, but on top of the P is like,
P prime.
yeah, right?
Yeah, that's the derivative.
So I have to take the anti-derivative one?
No antiderivative. I'm just going to take the derivative. Just gonna take the derivative.
The derivative of each.
Okay, let me just start doing it. And we'll see. Let's not guess. I just want to get into it. Let me get into it. So for the solution, what we need to do is we need to write down the form of a polynomial. And you've already got this in your notes, guys, because I have done these before. So you write down the form of your p of x, right? And what you're going to need to do is take the derivative of this and then plug in 3 and set it equal to 0. So I'm going to take the derivative of this general form, so 3ax squared plus 3bx plus c. That's the derivative of ax cubed plus bx squared plus cx plus d.
Should I be 2bx?
2bx. Is that better? Yeah, okay, thank you. 2bx. So that's my derivative. Now I'm going to plug in 3 into that. So everywhere I see an x, I'm going to put in 3. So I get 27a plus 6b plus c. And this I am now setting equal to 0. What happens now is that this creates an equation. And in this equation, notice that B, C, and D, they are all free. Like there's really just, if you wanted to think of it as a matrix, it would look just like this matrix here. And you only have the pivot on that A variable. So the B, C, and D are all free. And then I can solve for A in terms of the free variables. So if I solve this in terms of, in this case, it would be B and C, I guess. You'd have A equals negative 6 over 27 of B, and then minus 1 over 27 of C. Yeah. So what is your actual P of X? If I now go back and I plug in for A right here, in that original P of X form, I have negative 6 over 27B minus 1 over 27C times x cubed plus bx squared plus cx plus d. That's how the polynomial would look. Yeah, so my vector space consists of these polynomials, not just this thing here. If my vector space was P3 of R, this would have been all we had to write down. And we would have had busted out 4 free variables, and we would have had a 4-dimensional vector space. But as you can see, guys, when you bust this one out, you pull out the B, you pull out the C, and you pull out the D, right? You're going to see that the B has a negative 6 over 27 times x cubed plus x squared. And you're going to see that the C has a negative 1 over 27 x cubed plus x. So you've got this guy, and this guy. Everything in V is expressible in this form, which means how many basis vectors do we have for V here?
3.
Only 3. This is tricky. It's tricky because you see the P3 of R and you're thinking, oh, it's 4-dimensional because the dimension of P3 of R is 4. But my actual vector space V is not the whole P3 of R. It's only the subspace of P3 of R consisting of these polynomials. And so my dimension of V is only 3. It's a little tricky. The dimension of V is only 3. And how many vectors did they give us?
They give us 4.
So that's the K value of 4, right?
Yeah.
Okay, so now we have to remember, all right, when K is bigger than the dimension of V, so when I'm looking at my 4 choices here, when K is bigger than the dimension of the vector space, do you remember what we can cross off of the wrong answers just right away?
LA.
Cross off Li, and of course that means we have to cross off both as well, right? It's exactly right. Okay, so that tells me that these vectors in S right? They are either a spanning set or they are neither. I want to make sure everybody's good. So we're still not done with the problem, but are we okay up to this point?
So you said not linear because K is greater than.
Right. So here, I should write that down actually. So K is greater than the dimension of V on this example, and that implies that it's not Li. It might span V. That's the maybe. That's the maybe part of it, but it's definitely not Li. It's not Li. Okay.
Like if it wasn't given us those conditions, then we would normally just go about it like by putting it into a matrix array.
If this condition wasn't here,
Yeah.
it would have been very similar to the problem we did over here. The dimension would have been 4, K would have been equal to 4. We would have built this 4 by 4 matrix. We would have taken the determinant and it would have been both or neither according to what we got. So I didn't want to just repeat that again. So this is a slightly sort of a step up from that kind of example, because here, this vector space is a little bit harder to describe. Like, we don't know the dimension of this vector space off the top of our heads. We've never seen this vector space before. Like, right now is literally the first time we ever saw it. So how are we supposed to know what the dimension is until we actually do this work to sort of figure it out? That's what we have to do there. Yeah, Oscar.
A similarity that I saw with the example we did in the past lecture for P of 5 equals 0.
Yeah.
And I'm looking at this one as well. Can we imply that whenever we have a condition where it's like that, can we imply that somewhere in there there's going to be free variables?
What you can, if you want to kind of know the scoop, every time there's a condition here, it knocks the dimension down by 1. So like if P3 of R was 4-dimensional, but then I put one condition here, notice it knocked the dimension down to 3. If I had put 2 conditions here, it would have knocked it down even further to 2. And you can kind of, just as a rough guide, use that. I never said that in class formally as a thing to know about, but it is the way it works. Yeah, it pretty much works that way. Yeah, okay. So we've got a 3-dimensional vector space, but they gave us 4 vectors, which is too many. Shoy?
About the rule you just said, would you
Yeah.
say that's like a set thing that I should know, or?
No, I don't think so. I think it's better to just kind of go through this process. Also, because actually, I don't want to make this too complicated, but depending on what the conditions are, you could have exceptions to that rule. If I put another condition here that's actually more or less just a rephrasing of the first condition, then it might look like 2 conditions, and then if you get too hung up on this idea, you'll knock the dimension down by 2, but you really shouldn't have, because they're really the same. So I think it's better to just kind of go with the straight procedure that we just kind of went through right here. Okay. Question now is, will they be a spanning set? Because I've crossed off Li, I've crossed off both. Question is, are they going to be a spanning set for V? These 4 polynomials. Pretty good chance of it, because after all, V is only 3-dimensional, and we're already spending an extra $1,000 here. We're spending $4,000 on these vectors. Seems pretty like a pretty good bet that they have a good chance to be a spanning set. What do you guys think? Think they'll be a spanning set? I'm gonna tell you that they are. So the answer is going to be yes. Let me just give you kind of a rough reason why they should be. If you just look at the first 3 polynomials, just the first 3. Okay. I know, by the way, that all 4 of them taken together are LD. The 4th one is for sure LD with the other 3. But the three that I just circled in blue, they are actually Li. And how do I know that? Just by looking at them. I know that just by looking at them because actually, the first one covers the constant term. Well, actually, let me go back even easier. Even easier. The first two are not scalar multiples of each other. So the first two are Li, just the two of them. Oh, why is the third one still Li relative to those two? It's because the first two do not even have x squared showing up anywhere in the polynomial, which means that this third vector is adding something new that the first two vectors don't already have. So that means that this third one must be linearly independent from the first two. Well, guys, those three blue circled polynomials are already spanning 3 dimensions because it's 3 linearly independent vectors. So they have to be spanning the whole S already because the dimension of, they have to be spanning the whole V because the dimension of V is only 3. So I'm just going to make this comment. Note that the span of S is 3-dimensional. So the span of S is the entire vector space V. It's the entire universe of V. Yes.
So you're saying that basically like because we're given like 4 vectors and 3 of them are unique.
3 of them are Li. Yeah.
Okay. Well, basically none of them are scalar multiple each other, and they're creating the third one's adding to the first 2,
Correct.
which is making it unique.
Correct.
And because of that, you know that it only has to. Well, you only have to have 3 vectors in order to confirm the conditions of the 3 dimension.
Yeah. Yeah. These 3 vectors already span something 3-dimensional, and they're inside of V, which is only 3-dimensional. It's not any bigger than that. It's only 3-dimensional, so they must span the whole thing.
Okay.
Yeah. Yeah, I don't know if you guys remember, there was a homework problem a while back where I think I said something like this. This was in section 4.5. I think it was number 49. That said that if V1 and V2 is Li, and I take a third vector V3 that is not already covered by the span of those first 2 vectors, then I can throw that third vector into the set. I can make my set bigger. I can throw my third vector into that set and it will still be Li. You were there that night I did it. I was recording solutions to the homework problems, and some of you probably watched my video on that. And this was one of the sort of theoretical problems about linear independence that I did. If I have vectors that are Li, and I throw in a new vector that's outside of the span of what you already have, then the Li is preserved. And so that's kind of the way to think about this. The first 2 vectors, this is V1, this is V2, they are Li already. And this third vector, because it has an x squared in it, is outside of what the first 2 vectors would be able to span. So this third vector is still going to make an Li set. So you've got the ability right here, guys. You've already got the ability to span something that's 3-dimensional. Well, that's as big as your whole universe V is to begin with. So you are able, therefore, to span that whole thing. It's pretty cool. It's pretty cool. Okay, anyway, so I just wanted to remind you a little bit about that. So that's a trickier one. This is a tricky one. But let me just tell you, if you saw this on the exam, and let's say you completely blew this part off, because I remember I think this was just last semester. And I still remember grading it. There were a lot of people who said, oh, the dimension of V is 4, and K is equal to 4. And so they said, oh, it's both or neither. And they set up a matrix, do whatever, and they drew all the right conclusions based on that. I think in that case, they would have ended up saying neither, which is the wrong answer. Neither is the wrong answer. The correct answer should be spans V. But if they had put all of that other stuff down, they figured out what K was, They incorrectly got the dimension of V, but then they based the rest of their answer on that. I was giving partial credit, at least half credit, for just going through the rest of the motions correctly. So what I'm trying to say here, guys, is even if you're feeling a little thrown off by a problem, if this is throwing you off a little bit, write down what you do know about it, because I can give you credit for that. Tell me what K is equal to. Tell me, what the dimension of V is that you think it is. Okay, you might have it wrong. I'm going to dock you for that. But then based on that, I'm going to be able to grade you more favorably on your conclusions that come from that. Okay, because this one's a little tough. I think a lot of people in the class had trouble with this the last time I put that on a test. Yeah.
Kind of looking back on to number 49.
Yeah.
I know we went through the solutions and it's already posted, but just so I refresh my mind. So for that solution, can we write that, assume that vector 3 is a part or is an element of the span? Or is part of the span?
No, this is V3 is not in the span of V1 and V2. So you would not start by writing down the opposite of that.
Oh, okay.
What you would do is to prove that a set of, this is good to review. If I want to prove that a set of vectors is Li abstractly, so without using a matrix, if I want to just know what the definition is, basically I'm going to assume that I have a linear combination of those vectors that cancels out. So I could assume this about those vectors. And see, I'm writing it very abstractly. And then does anybody remember, what do I need to show if I want to show that the vectors really are Li?
That your constants would equal to 0.
Exactly. We must show that C1 and C2 and C3 would be equal to 0. That's what you'd be showing. Exactly. This is just the definition of Li in a very abstract setup. I know later on we figured out how to put it all into a matrix and just do EROs and circle pivots and do all that stuff. But when we're first trying to understand what the actual definition is, this is how it looks. Yeah, this is how it looks. So that's basically the setup of it. And in this case, we're assuming that V3 is not in the span of V1 and V2. So this third vector should be something outside of the span of the first two, which is what this problem situation is. Yeah.
Just so I can conceptually grasp Li. So you said that's the general abstract way of explaining that it's Li only if the coefficients or the constants.
The constants are all 0. Yeah. Yeah, that's it.
So then, if one of the constants is not 0, meaning it's a variable?
It would be like a free variable. Yeah, so if there was a free variable.
So then that'd be dependent of whatever the other constants are.
Well, that vector that goes with that non-zero scalar would be linearly dependent on the other vectors. So you'd be able to write down a linear dependency in that case.
So then let's say C3 is a free variable, so then C3 equals C1 with blah, 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 blah.
Well, if C3 was a free variable, I would call it T. And then I would back substitute it into whatever my equations were, and I would get C2 something in terms of T, C1 would be something in terms of T. I would bust out that T, and basically I'd plug in T equals 1 or something, and I'd get specific numbers for C1, C2, and C3. I wonder if we should do something like that, basically creating a linear dependency. Yeah, let me come back to that, but that's definitely something people need to be able to do. Yeah, for sure.
So let's say you were able to remember these kind of tells about dimension and the K. If you
this part?
Yeah.
If
you wanted to go on and then check if it's a span like the regular way,
how
would you carry on at this problem?
Okay, so you would normally put the if I wanted to check whether these 4 polynomials were a spanning set for V, I would basically want to, if I didn't know what the dimension of V was, right, then it's going to be challenging for sure, because I don't know how many vectors I need to span it. You can try that. The normal procedure is to lay your vectors into the columns of a matrix, right? So the first polynomial might look like that. The second polynomial might look like this. The third polynomial would be like this, I guess. And the fourth polynomial would look like this. So you would lay these out in the columns, yeah? And for spanning set questions, as you might remember, we normally will augment this with number symbols here, right? But there's a little problem with this. Again, it's because this is a little bit of a tricky question. If I'm putting these number symbols here and I'm saying, oh, anything could be in this far right column, then I'm actually testing not whether the four polynomials span V, but I'm actually testing whether they span P3 of R. Because if this was like an A, B, C, and D, then that would be ax cubed plus bx squared plus cx plus d. And so what's actually in this far right column, like I can already tell you the answer is going to be no. Those four polynomials are not necessarily going to be able to span P3 of R. They do span V, but not P3 of R, you see, because P3 of R is larger than V is. So this would be a little bit tricky, I should say. Actually, besides the fact it's a 4x4 matrix, which is kind of a pain to begin with. So, but yeah, the normal procedure is this procedure. Yeah. Yes, Oscar.
Could I, like, if I was gonna take that route, right, and I didn't know, maybe I forgot something, right? The procedure.
So you set up this matrix?
Yeah.
Yeah, no worries.
Can I do a lower triangle matrix and then take the determinant and then base my choice off that?
Yeah, you can do EROs long enough to get it in triangular form, and then from a triangular form, the determinant is just the product of the diagonal values. And as long as it's not zero, right, that's good. If it is zero, that's bad, and kind of go like that. Yeah, definitely. Okay, good questions. Sure.
That's the good, but otherwise I should be like able to make a conclusion by finding the dimension of the cube.
Yeah, being able to find the dimension of V and defining the value of K is really important. K is always really easy. There's never anything weird about that. You're just literally counting how many vectors there are. The dimension of V is usually very easy, unless it's some weird vector space that you've never seen before, right? Which would be something like that, where I put an extra condition here. So yeah, that's the thing to keep in mind. I think actually what would have been a better question here for this problem that I think would have been easier for my students, which is what I should have done, is instead of asking this question, what I should have asked is find a spanning set for V. That would have been a better question. If I asked to find a spanning set for V, all of this stuff in blue would have been good. It would have been totally correct. And your spanning set would just be these three vectors, right? And then I could have a part B to that question where I ask you, oh, are they Li also? And then you could go to the same reasoning again, you know, for example, these two polynomials don't have any constant terms in them. So this third one must be outside of the span of the first two, so they are Li. See, these three things that I circled, are a basis for this V, which is three-dimensional. But the polynomials that I gave out on the problem were not the three that were not the ones you ended up with here, which I think is what makes it a little tricky. I shouldn't have put this question there. Yeah.
And just like I guess like a quick little question for polynomial questions like that, you use the general
This guy.
yes. So whatever degree it's
Whatever the degree is. Yep. That's it. Okay. Great. Yes.
How did you know that it was how do you know it's a basis?
I know it's a spanning set because of the work that we did. We took this P of X, we incorporated the P prime of 3 equals 0. wrote down the general form of P of X, we busted out the variables, and then we would make our list, which would be these three things. So that is how you find a spanning set for a vector space. And then that's why I said the follow-up question would be, are they also Li? Because remember, to be a basis, they have to be a spanning set and Li. So they're already a spanning set based on what's the work is in blue here. And then they would be Li because they, well, for the Li part, you could put them into a matrix.
Yeah, I
would call them a matrix.
Yeah, I was asking like, how'd you make the like this? How'd you know that it's a basis? Because they both have the x.
It's the same. It's the same reason that I was giving earlier. If I just take these two polynomials only, they're not scalar multiples of each other yet. So these are already Li. And then this vector is not in the span of the first two, because the span of the first two has no constant terms.
Oh, okay.
So this is outside of that. And so all three of these together are Li. And so therefore they are both a spanning set and linearly independent, and they'd be a basis. That would have been a better question. Okay, can I erase this part? Yeah.
I was just gonna ask, after this example, are you gonna talk about null space, row space, and pole space in the terms of the way that it's on the worksheet?
Well, that was the first problem.
Oh, okay.
We already talked about that.
Yeah. I put it
Oh,
wrong.
that you should know, that handout, you should definitely know that, but I might not talk about that quite yet because I want to do some other stuff.
Yeah.
Okay, okay, so where do I want to go to next? Okay, I don't know how many of you have looked at the section 6.1. Has anybody in here looked at it yet? The 6.1 thing? Can I give you just a really quick overview of it, enough of an overview that we can then do a couple of examples from that section? I'm going to be going over it all on Tuesday, but I'd rather kind of make sure you're up to par with that right now. How many problems have I done? Only 3. Okay, so that's fine. So let me just say, guys, that what linear transformations are about, this is a quick crash course. So you guys will come in on Tuesday and you'll already know it. A linear transformation, I'm not going to do a long overview right now. I just want to at least give you the crash course version of it. I will always be denoting it with T. And it's a function. A linear transformation is a function from one vector space to another. So the V and the W are both vector spaces. So a linear transformation, again, this is just a very quick preview of what I'm going to be going over on Tuesday. A linear transformation involves an input vector space and an output vector space. So this is, mathematicians are always interested in functions from one world to another. So in this case, you could be plugging in polynomials and spitting out vectors in R5. Or you could be plugging in a 2x2 matrix and spitting out a calculus function. Or you could be plugging in a vector in R3 and spitting out a vector in P7 of R, right? So you have inputs from one world and outputs from another world. The only thing is, it's not just any old random function. It has to do 2 important requirements. T must do 2 things. The first one is respect addition. T must respect addition. Let me just write down how that would look on paper. It just means if I take T of, let's say, V1 plus V2, that it should equal T of V1 plus T of V2. So T respects addition. I like to draw pictures, by the way, for this here. So here's V, and here's W, and T is just your function that goes from the left side to the right side. And so you're plugging in, you got vectors over here, right? You're plugging them in and you're sending them over somewhere to the other side. Don't know exactly, something like that, right? It's just a function. Inputs and outputs, just like you would have seen ever since you learned what a function was. But the weird part here is that you're plugging in whatever these vectors are. They could be matrices, they could be polynomials, they could be calculus functions, they could be vectors with 17 slots each. It could be any kind of vector space. But the T must respect the addition. Okay? And you won't be surprised, it also must respect the scalar multiplication as well. So in a vector space, we have addition and we have scalar multiplication. So T of K times V1 should be equal to K times T of V1. And this is where K is just some real number. So these are the two conditions that define what a linear transformation is. It's a function that respects addition and scalar multiplication. It might remind you a little bit of showing that you have subspaces. So do you remember when, and we should practice some subspaces too, by the way. Do you remember when you have a subspace, it has to be closed under addition and it has to be closed under scalar multiplication. And that was one of the very first things we did in chapter 4. Here, there's two properties also that are related to those two operations. T must respect addition and T must respect scalar multiplication. As a side effect of that, there is also, I'll write this down as well, there is also a zero vector check. I don't know if you remember for subspaces. If the zero vector check fails, then it's not a subspace. So if the zero vector is not in your set, then you don't have a subspace, and you can say that right away before you even take a breath. There's a zero vector check here too, guys, which is that if T is linear, meaning linear transformation, this is just my short way of saying that. If T is linear, then it must send the zero vector to the zero vector. But let me be clear, the zero vector in V might not be the same as the zero vector in W. So I'm going to put little subscripts on these zeros to show that what that zero vector actually is, it actually could change depending on what kind of vectors you have in V versus in W. Okay. Ken?
So if the vector in the V word working, the W word is not working at all.
Working? Sorry.
Like, if the zero vector in V working.
So the zero vector in V, whatever it is, right? When I transform it, it must go under this function to the zero vector of W. If it doesn't, it's not a linear transformation. And if it's not a linear transformation, guys, there won't be anything else for us to do with it. It'll be the end of the story. So what would be an example of that? Well, if T, let's say that, just as a quick example, suppose that T goes from R2 over to P2 of R. Just, I'm making this up off the top of my head. And suppose that T of A comma B, so if I plug in some point with two slots, and let's say that I spit out over here some quadratic polynomial, let me make up whatever I want. How about A plus 3 times x squared plus bx plus 5a. Just making it up off the top of my head. And I can ask you, is T a linear transformation? So yeah. You gonna answer it?
Yeah.
Okay.
I don't think it is because it doesn't pass a zero check.
Let's check that zero vector check, right? Let's check it. If I do T of, what is the zero vector in R2? 0, 0, right? That is my zero vector. Now, if I plug in 0 for A and B into the formula that they gave us, what am I going to get here? 0 plus 3, that's 3x squared, and then plus 0x and plus 5 times 0, there's nothing else there. But notice what happened, guys, the output here, this is what the output would be, and that is not the zero vector of P2 of R. If I want to know what is the zero vector of P2 of R, which would be my 0 in the W space, it would be 0x squared plus 0x plus 0. That is the zero vector in the polynomial universe. But look what my function did here. It plugged in the zero vector and spit out not the zero vector. So this would be the zero vector check fails. And so it's not linear in that case. It's not linear. Okay. What we're going to do on Tuesday is, I'll start class by writing down the definition. And then I'm just going to do a bunch of examples of transformations. I'm going to have, is it linear or not, right? And we'll start by checking the zero vector. After we check the zero vector, well, then if it passes the zero vector check, well, then we have to go on and see whether it respects addition and scalar multiplication. It's going to feel very similar to checking the closure for a subspace. Yeah. I think with what I've put on the board there already, guys, I can already do an example from my handout. Excuse me. Let me try this one. So this is number, I'm going to call this number 4. Suppose that T is a function from P2 of R over to M2 of R. This means I'm going to plug in a quadratic polynomial and I'm going to spit out of the formula a 2 by 2 matrix, right? Let's suppose that this is known to be linear. Now, I should point out that I haven't even given you the formula yet. I have not even told you what T does to give me inputs to outputs. All I've said is what my two universes are, right? This is V, this is W. That's it. So what I'm going to say is known to be linear, and then such that, now I'm going to give you some values. Let's suppose that T of 1 is the matrix -1 and 2 and 0 and 0. And then the next one is T of X, not T of X. The next one is T of X plus 1, which is going to be -3 and 0, and then 2 and 1. And then lastly, T of X squared plus X plus 1 is the matrix 3 and -2 and 0 and 1. And what I want to try to do here, guys, is compute T of any quadratic polynomial, ax squared plus bx plus c. I'll let everybody write that down, and then we are going to do this problem. Yeah,
Is this section going to be on the midterm?
Oh, yeah.
When it comes to this idea of like transformation, there's a question that you put on the second Richard sample. It seems like so much more simpler, and is when it applies to this section, is it just you can just throw anything to it, like whether it's polynomials, matrices, because this one that you threw on the midterm, the practice midterm, you're just using the R's.
So it could be any V and W. It could be any V or W.
Okay.
Absolutely, yeah. So the V and W are any vector spaces whatsoever. Yeah. By the way, if T respects addition and scalar multiplication, then would you agree that it would also respect all linear combinations? In other words, if I had T of C1 V1 plus C2 V2 plus dot 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 plus Cn Vn, if I already know that T respects addition, and I already know that T respects scalar multiplication, do you agree that I can totally bust this out? And I can like pull the first constant way out and then do T of V1. And then I can do the second constant all the way out and then T of V2 and then go like that. It's literally just putting these two things together. Constants come out, the plus signs bust apart, and you just get a big long linear combination. If T respects the two fundamental operations in a vector space, then it's going to respect any linear combination that happens in that vector space. Yeah. And if you believe that, then this problem becomes really pretty straightforward. Any thoughts what I'm going to do to, by the way, this is amazing. I've told you T of 3 inputs. And somehow from that limited little bit of information, we're going to figure out what T of anything else is, which is so powerful. Yeah.
I don't know if I'm looking at this right, but can you use respect to addition and do like tx plus t, and then on that one tx squared plus tx plus t1, and
Yeah,
then use
we would be able to break these apart. All of those are apart. Yeah. But before we do that, let's just look at this. This is what we're asking to find. What can I do with this? Anthony? Yeah, so what's it going to be? A times T of x squared, good.
B times T of X.
Plus B times T of x. Plus C times T of 1. There you go. That's exactly right. So if it is known to be linear already, I'm trying to show you the power of having a linear transformation. If you have something that is already known to be linear ahead of time, then you can bust it out like this. And now I can just try to start plugging stuff in. Now the thing is, I know what T of 1 is. So I actually know that this last term, let me just come over to the last term for a moment. I know that I can do that last term directly because they told me what T of 1 is. But you might notice they didn't tell you what T of x is. Yes, Brandon?
When you define like T of x squared, you take the T of x squared plus x plus 1, and you subtract it from the T of x plus 1.
We can start doing some subtraction here, right? So if I want to know what T of x squared is, what I have to observe is they didn't tell us what T of x squared is. But they did tell us what this is, and they did tell us what this is. And if T is respecting everything, it's going to respect that subtraction as well. After all, subtraction is really just addition with a scalar of -1 in there. And T is respecting addition and scalars already. So I can literally just do subtraction here, right? So if I want to know, let me just do this off on the side. What is T of x squared? I can just treat it as this is T of x squared plus x plus 1 minus T of x plus 1. So you just subtract off. You rewrite the one that you want to know in terms of two of them that you already do know. And this just becomes whatever it is, this matrix 3, -2, 0, 1, minus -3, 0, 2, and 1. And you just calculate it out, right? So you're going to get 6, -2, -2, and 0. And that goes in way up here in front of the first term. So A times 6, -2, followed by -2, and 0. Just like that. Yeah, looks pretty good to me. And now I also need to figure out T of x. Did they tell us T of x? Doesn't look like it. Can we figure out T of x?
Yeah.
By doing what? this one minus this one again, right? Same thing, you just do subtraction. So this is plus b times, so I take the second one minus the first one. -3 minus -1 is actually -2. 0 minus 2 is -2. 2 minus 0 is 2. And 1 minus 0 is 1. So that would be it. Yeah. Now, you could leave that as your final answer, and it would be totally correct. Some people like to just combine it into one matrix, and I don't mind that. That's going to actually be useful down the road. If I just like read across the upper left corner of everything, I see a 6a, and then a minus 2b, and then a minus c. And then in the upper right corner, I see a -2a minus 2b plus 2c. The lower left corner is -2a plus 2b, and the lower right corner is just b. Does everybody see how I made this one matrix out of the terms of the line right above it? Yeah, that would be optional. Like this is also totally correct, but this would be just one extra step if you wanted to. Yeah. Does that seem pretty easy?
A little bit.
Um,
Because you're, for these problems, they're always gonna give us exactly what is it they want us to compute.
well, they have to, yeah,
Okay.
yeah, for sure, for sure.
And from there, you basically just start busting out the variables. And
The reason that this is relatively easy, I could make this a lot harder, but I probably wouldn't. If I was making it harder, I'd be making it harder just computationally. The way I could make it harder is I could start giving you some. I could say instead of giving you x plus 1, I go, oh, let's give them 8x plus 17, and then let's give them, I don't know, let's make it nasty here. Something like that, right? If I had given you those values and then asked you to like figure out like, oh, so what's t of x squared now? This would be much harder. But it wouldn't be harder in a good way that I would want to do because it's just going to be computationally harder. It's not going to be conceptually anything different. The reason that this type of problem is so easy, though, is because it starts off by saying, suppose it is already known to be linear, right? If you are assuming that your function is having these properties here, that is really powerful as a starting point. So, oh, t respects everything. So I can, do subtraction, addition, scalar multiplication. I can pull out constants. I can do all of that freely as like one of the properties of the transformation.
And you skip all of that.
And I wouldn't have, you wouldn't be doing any of this because it was already given to you, right? Maybe I should do one where it's not given to you. And then that'll be probably good enough for today on chapter 6. I just want to I don't want you to have to worry too much about it. This is not that bad of a chapter. This 6.1 is not really that bad of a chapter. So that's a good example of a problem right here. Let me give you one more.
Is that just like how deep we're gonna have to go on that section?
It's not going to be too bad. I'm going to do class on Tuesday for 2 hours. I'm going to do the homework from 6.1. You'll see exactly what it's like.
For them to
Yeah, it's not going to be too crazy. It's not going to be too crazy. Let's try this one, guys. Let's let t go from P2 of R over to P2 of R be given by t of p of x equals x times p prime of x plus 2 times p double prime of x. And what I want to do here, guys, is show that t is a linear transformation. I'd like to show it. On this problem, we assumed it was already known to be a linear transformation, and I asked you to calculate the formula for t. On the one we're going to do right now, it's completely the other way around. I give you the formula for t, I lay it right out here for you, but then I have to show that it's actually linear. So this is the other kind of question that you see a lot in this chapter. We've already done one example where the answer was no, right? This one, is t linear? It was no, because the zero vector check fails. In this case, if you do the zero vector check here, so what is my zero vector check? My zero vector check is if I plug in 0 into t, I should be getting 0 out of the other side of t. Does that happen with this formula? If I plug in 0 for my polynomial, then what happens when so I take x times the derivative of 0 plus 2 times the second derivative of 0. What are the derivatives of 0 going to be?
Zero.
Just 0, right? It's all just 0. This is 0 plus 0. So that checks out. This time it's totally checking out. So it does pass the zero vector check. So now I want to show you that it respects addition and scalar multiplication. Okay? You guys are going to have a nice advantage on Tuesday because you're going to already have seen a couple of these, which will make things really nice. So let's check that t respects addition. Now I got to kind of look at this formula. For respecting addition, I have to sort of plug in two vectors from V. And we are plugging in polynomials here that look like P of X. So I need two of those. So you can imagine what I'm going to do is I'm going to take a P of X and a Q of X, like two polynomials. So I might do that. Let's take T of, and let's just do P of X plus Q of X, something like that. Now, what I have to try to get to somewhere down here, okay, I'm just going to write it at the bottom for a moment so we kind of know what we're shooting for. We want to get the two terms separated, right? The right-hand side of my condition here is a t of the first one plus t of the second one are pulled apart, right? That's ultimately what we're hoping for. But we got to get to that point. The first thing you need to do when you see something like this, guys, is you need to actually, inside the parentheses, add these two things together. So this is actually, I'm not ready to do the transformation yet. I just need to add P and Q together into a single polynomial, which is just known as P plus Q. I really can't simplify it any better than that. It's just whatever the sum of the two things, P and Q, are. Once I've got a single input here, right, then this formula tells me how to deal with it. This formula tells me if I'm transforming a single input, what do I need to do? Well, let's just read it off. I have to take x times the derivative of whatever that input was, which is P plus Q prime of x. And then the next term is a plus 2. And then I see two derivatives of P plus Q as well. And so that would be the second part of it, just looking just like that. Okay. If I have two functions added together and I'm going to take their derivative, so if I had like, I don't know, e to the x plus cosine of x, and I wanted to take the derivative of that, Tim, you're back in first semester calculus again. How would you do the derivative of this? This one plus this one, right? You just do the derivatives separately. That's one of the properties of derivatives. So I can do that here too. I can treat this as P prime of x plus Q prime of x. I can break that apart, yeah? And actually that's also true for double derivatives. So I can do the same thing on the second term. P double prime of x plus Q double prime of x, just like that. By the way, that fact that you can split up derivatives across plus signs is really the reason I even have this job.
Seriously?
And if that wasn't true, if you could not split up a derivative across a plus sign, we would not be teaching differential equations with linear algebra. This course would not exist because you wouldn't be able to use linear algebra to help you with differential equations if, the addition and scalar multiplication was not respected by the calculus operations. So yeah, I'm kind of being a little dramatic about it, but yeah, this class would not exist if derivatives didn't respect addition and scalar multiplication. Yeah, Oscar.
I'm just curious.
Uh-huh.
Is this used in the practice, like in the real world situations?
Mhm.
And if so, where?
Yeah, so the power of this concept is already shown on that example. I have told you T of just 3 inputs. And based on that, I could tell you where all of the rest of the inputs go. So let's suppose that T is a transformation that rotates a graphic on your computer screen. So you have some image, and let's say you want to either rotate it, or maybe T could be a reflection across some axis or whatever. What this kind of idea is saying is, all right, if I want to rotate all the pixels, there's millions of pixels on this computer screen. If I just tell you that this pixel moved there and this pixel moved there, you can then tell me where all the other pixels get moved to, based on just that little tiny bit of information. So here I've only given you 3 pieces of information and generated out of it an infinite amount of information, right? Is that idea. So computer graphics is kind of the example I'm talking about here. But again, just in any place where you sort of have a basis for some, universe that you're working in, if you know how the transformation affects that basis only, you can use that to figure out how the transformation affects anything in that vector space. It's a pretty cool idea. Anyway, I don't want to get too deep onto that sidetrack right now, but I'll certainly be coming back to that point. Did you have your hand up?
Yeah, I having this problem in my final element.
Uh-huh.
They would like you analyze how an object would like respond to spread, would like little information.
It's pretty cool. Yeah, it's really cool. It shows the power of a basis too. Actually, if you're looking at P2 of R, 1, x plus 1, and x squared plus 1 is a basis for P2 of R. You guys could check that. You could make a 3 by 3 matrix, and I guarantee you the determinant would be not 0. If I tell you how T affects a basis, then that tells you how T affects everything. Super powerful idea. Anyway, I'm getting sidetracked. I got to finish this. The last step here, I have the P of X completely in the front and the Q of X completely in the back. Would anybody suggest an algebra step here for me, Brandon?
And you just distribute the x and the 2 out, and then kind of just
move things around a little bit. Yeah, this next step is just a little algebra. Guys, I'm going to put everything that has P of X in it towards the front. And anything that has the Q of X in it, I'm going to move it towards the back, right? So up in front, I've got x P prime of X plus 2P double prime of X. There we go. And then I'm just going to take the Q of X stuff and put it in the back. X times Q prime of X plus 2 times Q double prime of X. There you have it. And then actually, I perfectly led myself to the last step, because this one is T of P of X. This one is T of Q of X. Notice how I formatted this. I've got nothing but white space over here on the left side. I'm literally just making a column of algebra steps. This is good formatting that you're going to want to use. That's really good formatting. Okay, so am I done? What am I not done with?
You need to do the
scalar multiplication, exactly. So T respects addition, but I also have to check that it respects the scalar multiplication. Shall I do that too? Let's write it down right here. T respects the scalar multiplication. I'll just write it as a dot. T respects the scalar multiplication. Just gonna kind of put it like it's a dot. So how is that going to work? What letter do I usually use for my scalars? K, right? So let's start on the, in fact, I've got it right here, right? The K is right here. So let's just do T of K times P of X. The goal is to get the K out into the front. But you can't just pull it out, right? You have to actually do the transformation and derive that K can come out. So how does this work? Well, I just plug it into the formula again. X times K times P, sorry, it's X times KP prime of X plus 2 times K times P double prime of X. So I'm literally just replacing the P with the K times P as the input. So K times P just gets plugged in. We're using this formula right here that was given to us. And we're just checking that T is respecting scalar multiplication. What do you know when you have, if you want to take the derivative of 7 times e to the x, right? You have some scalar in front. What happens to the 7? Pull it right out, right? So I'm going to do that here too with the K, right? The K just comes right out. The K comes right out of the first part, which is X times P prime of X. And I can also pull the K out of the second term, which has the 2 there. So it becomes 2K P double prime of X. And what do you recommend I do for my next step? Totally factor out that K, exactly right. So we take the K all the way out, and put some brackets there to kind of factor it totally out in front. So the K comes all the way out. And as you can see, we are basically done because now we have K times T of P of X. And we kind of put, I usually like to put check marks on these when I get them verified. We end up with what we needed there. For this second step, the K has to be factored into the front. Brandon?
Do we just recognize that, like, you go from the first step to the third step without the second step?
Great question. By the way, I'm going to put my white space over here again. Yeah, so if you had skipped the second step and you just realized, oh, I can see that K is going to come all the way out into the front, and if you had jumped to the third step, I would have given you credit for that. Just be careful that you don't totally blow the whole thing off and sort of almost have nothing showing as, oh, well, here I started with this, I ended with this, and I almost have nothing in between. Make sure you do have enough steps in there to make it continuously flowing. But yeah, if I could believe that somebody could see that in their head and they skipped that step, I would totally go for that.
Could you just go from like the very first part where you have T times K times P of X and then just go straight to the answer?
From here to here?
Yeah.
See, if you did that, then you're like totally bypassing the problem. At that point,
But isn't it like, it's just, that's
it's true that you know, this is the conclusion.
Right?
Yeah. I'm just saying the question says show it.
Okay.
So if you sort of just given me where you're starting and where you're finishing and there's no work in between, I'm sort of like, well, do they really know what they're doing, or are they just writing down the condition? So I'd like to see that written out. Chances are, if I give you one of these, it's not going to be quite that you could just look at it and see it immediately, because it could be messier if I haven't, you know.
Yeah.
You can do this with matrices, you can do it with traditional vectors or functions or whatever the vector space is.
Actually, if the question is saying to show that it's linear transfer, that it's a linear transformation,
Mhm.
do you have to do both with respect to T and scalar multiplication?
Addition and scalar multiplication, you have to check them both.
Okay.
Yeah, you do have to check them both. Okay, let's do something else that we haven't talked about yet. I think I'm gonna leave it at that for this 6.1 overview for right now. There are some more things I need to say about it, but I gotta give you a reason to come to class on Tuesday. And on Tuesday, I'll show you some more stuff about it. Yeah.
So, quick question for the linear transformation. Is
Yeah.
zero vector check like a necessary thing, or is it just something that's like that?
It's something that makes it go by faster. You don't have to do it. And if it fails though, like it did on the one way over there, if that zero vector check fails, you get a fast no, and you don't even have to break a sweat. Yeah. If the zero vector check passes, then we've got to still go through the rest of the process. That's right. Oscar?
Yeah, I might have zoned out a little bit, but
Okay.
sorry, I might have zoned out a little bit, but you would always be given like for that example, you have T and then you have polynomial, and then you have over here T.
They have to give you this, if that's what you're talking about.
The equation.
The formula?
Yeah, the formula.
If you don't have a formula, then you're like flying blind.
Okay.
Like it doesn't make much sense to do a problem without having the formula.
Sounds good.
Yeah.
You did one of these problems on the midterm,
Uh-huh.
the practice one,
Okay.
and I see that you did like very, very little work. By any chance, could you explain that?
I did, it's just like that one, actually.
Really?
It's just like the one on the far right. It's just that it has a matrix instead of a vector in R2.
Okay.
So yeah, let me let you study that. We can go over it afterwards if you need to, but let me just leave it at that for now.
Okay.
It was because the zero vector check failed. So what he just found is a problem in my sample exam where it's just like the one I just did way over there on the far right.
Oh, because it doesn't equal zero, right?
The T of the zero vector did not give you the zero vector. So now you have proof that I've actually put one of those on my exam before, where the zero vector check fails on transformations. So definitely want to be looking for that. Because if I give you a problem like that where the zero vector check fails, I'm basically trying to throw you guys a bone. Like, here's an easy one. Let's get the points, check it off, and move on. Right. So be looking out for that.
I love that.
You like those?
Yeah.
We'll try. Let me give you another one here. Let's go to number 6. I want to know, decide yes or no if S is a subspace of V. And if yes, find a basis for S. Okay, and this is coming right off of last semester's midterm. So here we go, part A. My vector space is going to be C of 0, 1. These are the calculus functions on the interval 0 to 1. And S is going to be the span of the cosine of x, comma, sine of x, comma, 5 cosine of x plus 2 sine of x, comma, 7 times the cosine of x minus the sine of x. The first thing we have to figure out is whether this is yes or no, and then if it's yes, we have to decide, or we have to figure out what a basis would be. Do you have the answer, or okay, hold on just a second. Some people still writing down the question to give everybody a chance to kind of stare at this. It's a little bit long. So we're looking at calculus functions here, and I've given you 4 things, and I've said S is going to be the span of those 4 things. How many people think they know the answer, whether this is yes or no? Just raise your hand if you think you know already. Okay, I better wait another minute or so. I want everybody's hand up on this. I'll just give people another 30 seconds. You remember in class when I said, I think I'm starting to sound like a broken record?
Yeah.
Oh, yeah.
Okay, let's see if this rings any bells. How many people, raise your hand, do you think you know whether it's yes or no? It's a really fast one, you should just be able to glance at it and know the answers. Okay, Ken, what do you think? It is a yes, it is yes. And what is the reason, guys? Anybody? It's a span. Anytime you take the span of anything, it's always a subspace. You should just say yes immediately. A span, and that's all you have to say, is always a subspace. So this is another one of those problems where if you see something like this, I'm basically trying to throw you a freebie, right? Throwing you another freebie. It is a subspace. Now, the hard part of this question, if I can call it that, is that it does say that if it is yes, find a basis for S. So the basis, I mean, the four vectors that are listed here, cosine, sine, and then these two vectors here, they are a spanning set for S because S was created as the span of those vectors. So kind of by default, they are a spanning set, but are they a basis? Would these four things be a basis for S? I could think of, maybe this helps, I'll just label the first vector as V1, the next one is V2, and then we have V3, and we have V4. Do we need to spend $4,000 here?
No.
No, why not?
Is there scalar multiples? They're not, right?
I don't see any scalar multiples there, but remember that if I have more than two vectors,
Oh, yeah.
just being scalar multiples isn't the only issue. You can have dependencies even without that. Which way?
You just need cosine and sine x to make the other two, because.
Yeah, just kind of looking at it, guys. If I just spend $2,000 and grab cosine and sine, now these are not scalar multiples of each other, right? So these are Li right here. But the point is that the other two vectors are expressible as a dependency with the first two. In fact, you could note here that V3 is just 5V1 plus 2V2. That looks like a linear dependency. V4 would have been, 7 times V1 minus V2. That looks like a dependency. So you have linear dependencies here, right? So you need to throw these away. And your basis would just be the cosine of x and the sine of x. And these are not scalar multiples of each other. And so these are definitely Li, since not scalar multiples. So you could just say that. Wouldn't be any problem with that. Those are not scalar multiples of each other.
When we look at cosine and sine, we're saying that they're because they're not scalar multiples, that they're unique, right? But when you say that the V3 and V4 they're linear dependent, you're saying that like if you add one of those to cosine or sine, it's not really gonna like make it unique, or
Well, it just is redundant. It's
yeah.
you've spent $1,000 here that you didn't need to spend because you could have made this third vector out of what you already had.
Okay.
Same thing with the fourth vector. So let's not do that. Let's just pay only for what we need, which in this case would just be those first two vectors. Yeah. Now, remember that when we ask for a basis, it's never just one right answer. So you could have said, oh, I actually think I like the first vector and the third vector. And that would have been okay as well. Because the first and third vector are not scalar multiples of each other, and then you could build the other two in terms of those. But the point is that you should only have two basis vectors here. It's a smaller subspace than it looks like it is. I basically when I wrote this question, I remember exactly what I was thinking. I was like, let's give them an obvious basis, and then let's just throw in some extra garbage here and see if everybody knows that they should be throwing that away. These two vectors are literally just buildable out of the first two. There's no reason to add them to your basis. Yeah. So okay, good. So that I think you guys did pretty good on that. Let's try another one of these.
Those are pretty solid.
Not too bad. Not too bad. Yeah. Let's try another one.
I think Brandon has a question.
Question, Brandon. Yeah.
Say like V3 was tangent of x, right? Would that be a basis then with all regular basis, or because you can make tangent from sine and cosine, then have not?
Okay, this is a good question. What if that was my set of vectors? The question, what he's asking me is, would that be a basis for whatever this S is? It is true that you can write tangent in terms of sine and cosine, but not in the way that a vector space allows. A vector space only allows you to do addition and scalar multiplication. So tangent of x would be sine of x over cosine of x, and this is not something that you're allowed to build out of these two. Okay. By the way, you might be wondering, well, how would you know? How would you confirm that these are Li? Because there's too many of them to just use the scalar multiples reasoning. Can't do that. I don't know how to put them in a matrix. Can't do that. If I try to, set up a linear combination, it cancels out. Looks a little shaky as well. Actually, the answer to the question is we haven't really talked about this vector space very much. And we're going to learn in chapter 8, when we go back to differential equations, how we can test something like this for being Li. So that's still in front of us a little bit. But it's a really good question. I'm glad that you asked that one. Okay. Let's see. Let's do another one. Part B, I guess. Part B up here. Everybody hanging in there okay? We can always take a little break if you want. Or I can just crank through. We're making good progress. There's a few more things I want to go over, but I'm feeling pretty good.
I'll take a 5.
Crank through.
I just wanted to know, like, the review session for Wednesday, are you going to do something very similar to this? Or
Yes, I'll be doing very similar problems. On Wednesday, I won't need to go over the linear transformation stuff from scratch because everybody's going to have seen it. So I'll be able to maybe do a few other things. What's that?
like from the earlier stuff, like,
Well, yeah, I mean, I'll probably still do some linear transformation stuff, but I won't need to give you guys a crash course on it. So it might be a little bit faster. I mean, I never know exactly how these reviews are going to go, like, because everybody asks different questions. So, but I'll definitely take a video of it also, and I can also send out, when I send it out on Wednesday, I can say, well, here's something where it went in a different direction. If you don't want to come on Wednesday, I can say, well, here's where you should watch because you maybe didn't see it on Sunday. Yeah, something like that. Okay, let's do this one, part B. Let's do V equals P3 of R. And S is going to be the set of A minus 2x plus bx squared plus cx cubed. And then this is such that A, B, and C are in the real numbers. And the question again is whether that is a subspace of V. And if it is, we want to find a basis for it. This time we don't see the word span up there. And if we saw the word span, we've learned, I hope by now, a span is always a subspace. So this time it's not quite that fast, but what do you guys think? Do you think this is gonna make it as a subspace? I see some people saying yes and some people saying no. Let's maybe think about it a little bit more. If you added 2 of these gadgets together, would you get something that looks the same form?
Yeah.
Okay. Let's see. Zero vector check. I heard somebody say zero vector check. Should we do that first?
Yeah.
I would like to do that first. What is the zero vector in this universe? It would be 0 plus 0x plus 0x squared plus 0x cubed, right? Is that in the set? It's not. It's not because of
The -2.
that's the problem there, right, guys? Everything else is cool, but that -2 throws it off. This is not in S. And so this is also me throwing out a sort of a freebie. It's a fast no. It's a fast no. If the zero vector check fails, guys, it's a fast no. Whereas if it's a span, it's a fast yes. Okay, so that's really helpful. Yeah, Anthony.
I don't see why that is.
So the point is that the zero vector is literally this, right? And if you ask yourself, is this thing in blue going to fit the form of what the vectors in S have to look like? You would be hard pressed with this X term because for the zero vector, the X term is 0 in front of it. But here it's not 0. So it's not compatible with the required format here. See what I mean? It also fails to be closed under addition. If you added two of these things together, you'd end up getting a negative 4x. And that's not the right number there. It's supposed to be a negative 2x. You guys remember the homework problem? There were actually two of them, and I assigned them back to back. I think this was in 4.3. Might be number 19 and number 20. And they gave you two different subsets on 19 and 20. The 19 was like the set of p of x of the form ax squared plus b. And then on number 20, it was a set of p of x equals ax squared plus 1. And I was asking you in both cases, would these polynomials form a subspace of V? And then would these polynomials form a subspace of V? And as similar as they look, when you write them down, you think, oh, it's almost the same thing. But actually, this is yes and this is no. When you have general variables as coefficients representing your vectors, usually that allows for a very flexible type of form that you're going to expect to get. So if I add two things like this together using generic variables, I get something that still has generic variables in those terms, and that's great. It's going to be closed under addition. But if I put specific numbers in, so as soon as I change that b to a 1, now I'm in big trouble. If I added two of these together, I get something x squared plus 2. And plus 2 is the wrong thing to add. Adding a b is a flexible value. It's a variable. It means it could be anything. So if it gets doubled, there's no problem with that. But if I double this 1 into a 2 by adding two things together, that does not work because the 1 was supposed to stay as a 1. You see the difference? Yeah. Not to mention that this one fails the zero vector check, whereas this one passes it. So just be, if you're looking, I think students sometimes they like sort of just hard and fast rules, like quick little rule of thumb. If you see constants being built into the form, whether it's in, or it could be also for a matrix, right? You could have A, B, C, and then -2, right? Is that a subspace of M2 of R? Well, this is the problem right here. If you see constants that are built into the form of your vectors, that's usually a red flag. That usually means it's not going to work. I'm just giving you a rule of thumb, right? Whereas if it's all filled with variables, then usually everything is good.
Yeah, but coefficients are okay.
Coefficients like A, B, C is okay. Constants like that, yeah. Arbitrary variables, I don't know what you want to call them, parameters, variables, whatever. Those are usually going to work out nicely. It's when it's specific numbers that so often things don't go well. Yeah, unless that number is a 0. Now, if this was a 0 here, then I would be okay with that because, of course, 0 plus 0 is 0, and 0 times anything is 0. So it would pass the addition and scalar multiplication if it was a 0. But if you put any other number there, and watch out, guys, I can be sneaky with that. If you see like some constant has been fudged into the expression somewhere, that's something you should take a breath, pause, and look at it carefully because it might be that it's that thing that's throwing it off. Yeah.
Oh, maybe I forgot or something, but have we done problems where we're checking if, like, you give us like a matrix and it's to check if it's a subspace?
Oh yeah. We have the one that I really liked. I don't know if you remember, 2x2 matrices whose 4 entries add up to 0.
Oh, it's like
remember that? You know, like A and then B and then C and then negative of A plus B plus C. Show that that's a subspace, right? So you can do problems like that. Yeah, for sure we've seen some examples of that.
But like let's say like you give us a matrix and it's like A x squared, like you start adding like those other variables, like if it was like a polynomial.
I wouldn't put polynomials into the matrix.
Oh no, you wouldn't?
No, that's what students sometimes do that I have to get my red pen out for.
Okay.
No, the powers of x, they never go into the matrix.
Okay.
Right. Yeah, try not to mix polynomials with matrices. They're kind of totally.
Like let's say you want to lay them out, like so that you go from a matrix and you want to lay them out like that, like in one shot. So that you can perform those like closure addition and stuff like that. Like how would you do it?
You really shouldn't do that. If you wanted to check if this was closed under addition, you should leave them in the form they were given to you. So you should just take something like that and then come over here and add another one. Let's say, so this is still an X.
Oh, it's because I meant like if you're given the matrices, not like the polynomial.
Okay, whether it's a matrix or whether it's a polynomial, it's the same process.
Just add them. Okay.
Yeah, it's the same process. It's just how the vectors actually look. But yeah, so for closure under addition, you would add these together and you'd realize, oh, I get a negative 4x out of that. That's the wrong form. Yeah. Anthony?
What if you just add like -2 times d times x, then plus everything else?
-2 times d times x.
Yeah.
Oh, you mean right here?
Yeah.
Oh, if this was a 2dx?
Yeah.
Oh, now you've put a variable in there and that changes the whole story, then this would become a subspace. Because you'd have like a 2dx and then this would be like a 2zx, right? And then when you come over here, you get, a plus r, and then you get you get -2 times whatever times x, right? Plus c plus s times x squared, and then b. And then this is messy when you actually want to check the whole thing out, but you write that all out and say, yep, it's the right form. It lives in S, and you check it off. Yeah. So anyway, so the two that I put up here are really easy. I guess last semester I was going soft because this is a fast yes, and this is a fast no.
You can't go softer?
I can't go much softer than this. Fast, yes, because it's a span. Fast, no, because it's failing the zero vector check. So do I need to do one that's a little more? So what would be harder would be when you have no way around actually checking the closure under addition and scalar multiplication. Like there would be examples like that. Should we do one of those, or do you feel?
Is that something that you're like thinking about putting on an exam?
Of course.
So
You have to ask? Yeah, maybe we should. Maybe we should. I don't want people to feel like I didn't cover the stuff in the review session. I could ask you that. So let's. I just don't know that I see one. Actually, I'm sure there's one on one of those sample exams because usually.
No, there's not. That's right, Jack.
I checked. Right.
He wrote it.
Right. I believe you.
I wrote the group.
Okay. Let's do an actual example. So how about this? Okay, so here's an example. What number am I on? 7?
7. Yeah.
Let's do this. Let's let V be equal to M2 of R. And S is going to be the set of matrices A, which is in S. It's in V, sorry. The set of A in V. So it's a 2x2 matrix such that the trace of A is equal to 0. Now I'll remind you what the trace is if you don't remember. So this is one we haven't talked about too much lately. The trace is just the sum of the main diagonal. It's the sum of the main diagonal. So the question is S a subspace of V? Yeah. So if the diagonals add up to 0, basically. So it's not expressed as a span. It doesn't look like anything I've seen before. It's kind of a new problem. So what should I probably start with?
General solution or general matrix. General form.
You're getting ahead of me here. Getting ahead of me. What's the very first thing I should do? The zero vector check. I would just start with the zero vector check. In this universe, what is the zero vector? Just a big matrix filled with zeros, right? So you're just going to do 0, 0, 0, 0. And you're just going to look at it and ask yourself, is that in S? meaning if you add up the main diagonal values of this matrix, does it add up to 0?
Yes.
The answer is obviously yes, and that's very obvious. Just be sure you write element of S on that for me, so I don't have to get out my red pen and add that for you. It should say that on your solution, element of S, okay? All right, at this point, it passes the 0 vector check, so now I have to do closure under addition. Okay, so let's do this one. We actually have to write it out. So for closure under addition, I have to grab 2 vectors in S, and then I'm going to add them together and see if the result is still in S, right? So I'm just going to say we can use A and B, the elements of S. And I eventually want to look at A plus B, but before I can do that, I kind of need to get my hands on the individual matrices A and B here. If A belongs to S, then see, this is the hard part. This is the part you have to practice, is you have to write down now what A looks like. If its diagonal adds up to 0, then sum of the main diagonal is 0, then whatever is in the upper left corner, the negative of that should be in the upper right, or the lower right corner. Okay, so I might use a little a and then a negative of little a. Now the other entries could be anything. I don't have any information about those. I'll just use a B and a C. But the point is the lower right corner must be the negative of the upper left corner so that this trace is adding up to 0. Because that's the definition of the trace. I'd probably give you this reminder on the exam because we haven't talked much about the trace so far this semester. Yeah?
Right, general form.
I know what you're saying. I'm gonna come back to that. I'll come back to that in just a second. So let's just finish what I'm doing here. So I can write A like that, and then I'm gonna write B. It's also in S, so it should also have the same format, but guys, be sure to use different letters, not the little a, B, and C. Let's go with maybe, I don't know, X, Y, and C, and then we would have maybe negative X here. So we could write our A and our B like that. Now, if you use different letters, and maybe you use R's, S's, and T's, or maybe you decide to use F, G, H, doesn't matter what the actual letters are that you choose, but you should keep them very general here, right? Once you've written down the A and the B, then we're going to look at A plus B because we're trying to check the closure under addition. And I'm going to just add these together. So the upper left corner is A plus X. The upper right corner is B plus Y. On the lower left, I would have C plus C. And on the lower right, I would have the negative of A plus X. And we just have to write that down and stare at it and ask ourselves, is it still going to be in S again? Does the trace still give us 0? If I add the diagonal values, I think you can see that the lower right corner is just canceling the upper left corner. So the punchline, though, that will get you full credit is if you do write down that it's an element of S, that really needs to be there because that's the conclusion you're trying to draw. Okay, so it is closed under addition, and that part does check. All right, and then is everybody okay with that? And then I've got to do the scalar multiplication. So let's just do that one over here. This is where I have to grab a scalar k. Yes, Raphael?
I was gonna say, when we check if it's a subspace, it's because when you perform the closure under addition, it's supposed to revert back to its original form, right?
Yes.
So when you add those, like the A plus X and then that's like those two guys, you're gonna get 0. So how are you getting back to the original form?
When you add the upper left and lower right, you get 0?
Yeah.
Well, yeah, that is the requirement for the original form.
Oh, because it's tailored into under that condition.
Look at both of these matrices have that same condition. When I add the diagonals, I get 0. Yeah. Oscar?
So then for like the solution, can I also do like the trace of A plus B equals 0 and that be okay as well?
If you just wrote trace of A plus B equals 0 with nothing else, then you're kind of not showing your work, I would say. Like
After that?
Oh, after this?
Yeah.
Yeah, if you wrote that down, that would be okay. Yeah, you could say, thus the trace of A plus B equals 0, and thus A plus B is in S, I would buy that. That would be totally okay. Yeah. Yeah, good question. On the scalar multiplication, you just grab your scalar. I usually call it K. And then I usually just say something like, let A be as above. So it's just the same A that you already wrote down. And then if we just do K times A, if I just now get ready to do the actual scalar multiplication here, K times A, that's just going to be Ka, Kb, Kc, and negative Ka, like that. So just throw the K into all the entries, and we would just did that. And take a breath, stare at it, ask ourselves, is the trace of this matrix still adding up to 0?
Yes.
It is, right? That's kind of clear. Upper left corner plus lower right corner cancels out to 0. That is in S. So it is a subspace. Everybody good with that? Oscar.
Again, I'm just going on notation. Can I do a trace of K times A is equal to 0?
Yeah, for same thing, kind of what you were saying before. Yeah, so the trace of K times A is 0, and so Ka is an element of S. Do you guys notice I keep writing element of S all over everything here? That is absolutely non-negotiable. If you don't say element of S, I'd probably go take something off of it, because that's actually the punchline of what you're trying to show. Yeah. Is everybody good with that? Yes.
So if it fails either one, the addition or the scalar, then it's not a subspace.
Then it's not a subspace, and you could call it a day. You could be done. Yeah. Shoy?
I just have like a little problem with relating the span to the basis to like the vector space itself. So I just want to check like that I have the right understanding. So would you say that the basis is like a part of what S is, and then the span is just a part of what V is?
That's fair. Yeah, that's fair.
It's not
The
like-
basis is just a set of vectors, and when you take the span of that basis, it spans your subspace, which is inside of the big universe vector space V. Right. And yeah, that's
Yeah, like the size of things. I'm just trying to.
it's totally a reasonable thing to think about. Yeah. I mean, in terms of like a visual, here's your big universe V, right? And somebody's given you 3 or 4 vectors here, right? So this could be S right here. And then the span of S is all possible linear combinations of those vectors. So this is the span of S, which is a subspace within V, if think of it that way. By the way, yeah, go ahead.
The basis is smaller than this.
Yes, the basis is just a list of like 3 or 4 or 5 vectors, right? It's when you take the span of that basis that it suddenly blows up into this huge shaded in circle, which is now an infinite subspace of the universe V. Yeah, that's very true. I have a quick question, and Yair, you can't say anything because I know you know the answer. Would there have been another way to do this problem that we just finished over here?
Generalized form.
Write the generalized form. I actually did that here, and then do what with it? Bust out the variables, right? So let me just give, this is like a solution number 2 to that same problem number 7. This is another way to do it. I like it, Anthony. You're all over this. If we just write out our matrix A, B, C, negative A, and what he told me is to bust out the variables. If I do that, so I'll bust out the A, I get a 1, a 0, a 0, a negative 1, and then I get plus B times a 0, a 1, a 0, and a 0, and then plus a C times 0, 0, 1, and 0, right? And then what am I going to do next? And then I'm going to say that S is just the span of those 3 things. because you're taking all possible linear combinations of those three matrices. That's absolutely true. Yeah. And so why is S a subspace of V? That's because it's actually a span. It's the same reason we gave on the first problem over there. Anytime you have the span of anything, it's always a subspace. It's just that on this problem, it was not presented to you as a span. You had to do this work here that Anthony just led me through to be able to represent S as a span. Okay. Now, before you ask your question, I'm going to say one last thing about this, which is you might be thinking that you should be able to always do this on every problem. Can't you just say, I don't really want to do the closure under addition and scalar multiplication? Would it be possible for me to always just figure out the general form? Okay, we have to do that anyway, but just figure out the general form, then bust it out, make my list, and put the word span in front of it. The fact of the matter is that works a lot of the time. But there are situations where the problem isn't that simple. Like what if S was the set of functions, say f of x, such that, f double prime of x plus 5f prime plus 8f equals 0. Maybe I give you a differential equation. Well, I'm not going to know what the form of this f of x should be. So I won't know how to get to this first step of writing the general form. And so if I wanted to show that this forms a subspace, I really do need to know how to check closure under addition and closure under scalar multiplication. And I might on the exam, I think I've done this before, where I've just said, show that you have a subspace by verifying closure under addition and scalar multiplication. What I'm trying to say is I want everybody to be able to do this no matter what, because this is actually sometimes the only thing you have to go off of. So it's important that people in this class are able to confirm closure under addition and scalar multiplication. Okay, so I wanted to say that. Oscar and then Kim, you had a question, or do you not have a question anymore?
Oh yeah, I was gonna ask, could you end the exam ask, is S a subspace of B, and if so, what's the spanning set?
Yeah, that would be a great follow-up question. Well, it's kind of what I asked here. I said, if yes, find a basis. Part of a basis is having a spanning set. So your answer for that would just be this right here. So you would have been doing this part anyway. Yeah, so you can, unless I specifically say verify that it's closed under addition and scalar multiplication. If you can just do the solution number 2 approach to your problem, I'm good with that. If we go back to the set of P of X such that, what was it earlier? P prime of 3 equals 0, right? If you want to just write down the form of the vector there, bust out the variables and make your list, and that's your span for your subspace, you can do that. Absolutely true. Kim had a question, and then I love all the questions, by the way. This is great. Go ahead.
Is this similar to the number 15 of the homework on Friday?
Not this past Friday, no. We're not even in that chapter right now. Yeah. Yes.
So that's your question. So right here you wrote that you have f double prime and then 5.
Just made this up.
Yeah, you just made that up.
Yeah.
Right? Well, when you do the 0 vector check and then the closure addition, you're doing it the same way, right? Whether you have primes or not.
Yeah.
Same.
So 0 vector check would just be 0 prime plus 5 times 0 prime plus 8 times 0. Does that equal 0? Yes, it does.
Okay.
So it checks.
My second question is that could you do it where if we didn't have the trace?
And I had nothing there?
Yeah, would your matrix in the bottom right where you have A equals that, would it just be A, B, C, and D?
Yeah.
Okay.
In that case, you don't really have a subspace. In that case, you have you're talking about the entire universe of V.
Okay.
Because in that case, if you don't have, if you take this away, then you have nothing left except just A's and B.
Okay.
So in that case, your S is equal to V. It's kind of a silly problem at that point. There's nothing really to show about S because it's just the same as V.
But usually you have a condition.
I usually do. For a subspace, you would expect that.
Okay.
I mean, if I don't have a condition, then I'm really just talking about the big vector space V,
Okay.
in which case I might as well not even use the word subspace. It doesn't even make sense then. Yeah. Okay. We've got about 30 minutes till I think I said I was going to stop. I would like to do just a little couple of things from my true false section of my last midterm from the fall that has a little bit of conceptual things, and especially with chapter 5 and 6. So can we do that? And then
That's
we'll
like
then we'll
inner
call it a
product,
day. Yeah, I want to do a little bit on. I haven't really been talking about the inner product stuff very much today, guys. Partly because we just learned it, and I'm hoping that it's a little more fresh, like the Gram-Schmidt process. Can I get away without like going through all that?
You're gonna put the formulas, right?
I'm gonna give you the formulas for them. You just have to know when to use them, and it's just a calculation. It's not that bad, but I'm happy to do one if people want me to. But I think I'd like to. I'm really doing my best to try to focus on what I think people will have the most trouble with.
Yeah.
So let's try and do. Can we try and do a little proof here? Let's prove. Oh boy. Whew, now we get to the fun part. If the set of U, comma V, comma W is an orthogonal set, if it's an orthogonal set, I would like to show that if I take the norm of U plus V plus W all squared, that it would be equal to the norm of U squared plus the norm of V squared plus the norm of W squared.
Well, it is true, right?
It is true. If I say prove it, then it means it's true. I'm not very likely to ask you a lot of true false questions. If I did, I'd probably tell you this is true or that's false or whatever, and give you some guidance about that. I hated true false. Do you guys have professors that give you true false questions? And then they're always tricky, right? And they're always like, there's always like some little, they catch you on some little technicality. I hated that. I was pretty good student most of the time, but as soon as I got to the true false section, when I was a student, it's like, oh my God, I need a lot of help to get through that section. Yeah, Kim?
Would you able to like substitute into like a number and then like this if it's true or not?
Again, this is true because I'm asking you to prove it. We don't have any numbers here.
Like
So-
can you like make up a number?
You should not, if it's true. If this was a false statement and I asked you to show that something was false, you could make specific examples to show that it's false. So like if okay, I'm kind of going off topic here again, but just for a moment, if I gave you this, and I said, is that a subspace? They're kind of going back to the old questions. This one is not a subspace, and that's because closure under addition fails. It does actually pass. I know I've done this example before. It does pass the zero vector check, but it does not pass closure under addition because, so now here, Kim, this is where you could make specific numbers, right? There's an element of S because the determinant is 0. Here's another element of S, right? But then when you add them together, right, you get something where the determinant is not 0. So the closure under addition fails. So when you have some closure thing failing to be true, you can show it with a very specific example. That makes sense? Okay, great. Let's get back to this problem. How can we start working on it?
But you just take the magnitude of it and then just square it
Let's just leave it as is.
as is.
As is. Do we remember the formula for the norm? Let's just make any vector here. What's the norm of a vector formula?
Oh, isn't it because when you take the magnitude and you square?
Go ahead, Brandon.
It was square.
Square root of
It was the inner product of the
inner product of x with itself, right? Everybody's gonna know that solid, right? Super critically important. Yeah, so it's just the square root of the inner product of the vector root itself. So if I square both sides, then I get rid of that radical. Oscar?
Again, I keep going back to notation, but I was gonna ask, can you also say just vector x squared, or does it just have to be the end product like that?
This, I see it on exams all the time, and this is definitely a red pen moment. Because you can't take a vector times itself. This is when you square something, it's like multiplying by itself. And that doesn't make sense in a vector space. Like the only things we can do with vectors is add them and scalar multiply them. I'm not allowed to take a vector times itself. Right, guys? So can I get everybody in this room to promise me that nobody in this room is going to write something like this anywhere on your test for 2 hours on Thursday? I do not want to see this on any paper or this, anything like that. Yeah? Shouldn't be there. What you probably mean by that is you probably mean this. Right? This is correct. This, on the other hand,
No.
Does not work. Does not work. Speaking from experience. Okay, but nobody in here will do that, I'm sure. Okay, so let's go back to here. I've got something squared, the norm squared. So I've got my formula here. Let's just plug it in. So on the left-hand side, if you don't mind, guys, I'll just write LHS. Left-hand side, which is just this side, I'm just going to take the inner product of U plus V plus W with U plus V plus W. Right. Okay, so it's just the inner product of whatever's inside those double bars with itself. And what can I do with this thing here? Levi?
You can use like the axiom that says you could take stuff out. Like,
yeah, so we have these axioms for an inner product. By the way, I probably should be reviewing those again. The axioms for an inner product says basically you can bust apart plus signs and also scalars. We don't have any scalars on this one, but if there were, you could pull those out. But this is basically foilable. Like you can foil this one out. The inner product of U with U, the inner product of U with V, inner product of U with W, and so on. We can pull on both slots, actually. Right? Because we showed that you can do this in both slots. So actually, when you FOIL this out, you're going to get 9 different terms, right? So got to get our pens ready to write this all out. I have the inner product of U with U, plus the inner product of U with V, plus the inner product of U with W, plus the inner product of V with U, and then plus the inner product of V with V, plus the inner product of V with W, and then we're still not done, plus the inner product of W with U, and then plus the inner product of W with V, and then plus the inner product of W with W. Okay, so it's going to look like that. 9 terms when you completely FOIL it out. Yeah. Okay. And now what am I going to do to, it looks like I've made a real mess for myself. What can I do with that? Yeah, so some of these are the same, like these two are going to be equal, and same thing with UV and VU, those are going to be the same, and then the WV and the VW, those are going to be the same. So there's some repeated terms here. That's definitely good to know as well. Anything else that we could do to help ourselves get this cleaned up a little bit? If we were stuck right now on the test on this problem, what I would recommend is do not erase what you already have, because this is actually correct, and I can give you points for every part of the solution that you were able to write down. So just leave what you have and then maybe go on and then come back a little later if you're kind of stuck on it. But it's also good to just reread the question. Is there any assumption in the question up in the black writing that would be helpful for us at this stage of the game? It's an orthogonal set. Now, what does that mean? It means that U is orthogonal to V, U is orthogonal to W, and V is orthogonal to W. Any two of these are orthogonal. And what's the inner product of two vectors if they're orthogonal? 0. 0. So guys, the inner product of U and V is actually 0. The inner product of U and W is 0. V and W, 0. V and W, 0. W and U, 0. W and V, 0. Those are all 0. Almost all of the terms are 0. The only ones that you cannot cancel out are the very first one, which is the inner product of U with itself, and then the inner product of V with itself, and then the inner product of W with itself. Those should not cancel out, but all of the others do. All of the others do. Yeah. Make some sense? And now when you look at where we're trying to get to the right-hand side, do you see how we're going to get there? What is this term here? The inner product of U with itself is the norm squared of U. It's what's over there on the far left, right? So this actually just gets you right to the conclusion. So that's actually the whole solution is just right there. Okay, so it's a little proof. Usually if I ask something like this, it's not going to be real long. It's usually not going to be worth a ton of points, but it is for sure a likely thing I might ask something like that. By the way, if I did not tell you it was an orthogonal set, then you would not be able to cancel out these 6 terms in the middle, and you would have to figure something else out. Maybe I would give you some other information instead. Yeah.
What if like not orthogonal set, but like orthonormal set?
Oh yeah, what if it's an orthonormal set, guys? Orthonormal set tells me that the norm of all of those vectors is equal to 1, which would just mean that this would have been 1 squared plus 1 squared plus 1 squared, which would be adding up to 3 in that case. And I probably, if that was the case, so if I wanted to make a new problem, this is Kiem's problem. If UVW is an orthonormal set, show that the square of the norms of the vectors adds up to 3. Yeah, and then you can just do that.
And that's when you would have the vector, like for example, vector U over the magnitude of U.
But if it's given to you as orthonormal to begin with, then you don't need to divide by anything. It's already normalized. So you wouldn't need to do that. You just need to put in 1s for these terms.
Oh, okay.
Yeah. So that would be another variation on that question. Yeah. You'll see examples of those for sure in other places. I've used those a lot, I think. Okay, let's do another one. You guys ready for another problem? All right. I'm going to do another proof. That's okay. These proofs, guys, they're always very short. They're always very short. We'll just finish up in the next 15 minutes. I think we'll be in good shape. So here we go. Let the set V1, V2, and ... up to Vn be a basis for V. So start off with a basis for V. And okay, I'm going to go back. I'm going to press my luck on this linear transformation topic today. I know we've barely learned it, but let's just suppose that T going from V to W is linear such that T of each of these basis vectors is the 0 vector for all I. So I'm writing down, it's getting a little intimidating because this is a lot of words, but this is nothing very deep. It's just saying, assume that T of V1 is 0, assume that T of V2 is 0, T of V3, if you plug any of those basis vectors in there, assume that it gets to 0. Then what I want you to do is show that for every vector v in V, T of V is also 0. Almost takes longer to write the question than it does the answer, as we're going to see. I like this problem. We're assuming that T is linear. Okay, so let me just remind everyone, because we barely learned this. This just means that T already respects addition and scalar multiplication, right? So that's what we're going to review on Tuesday. But a linear transformation should respect both addition and scalar multiplication. What this problem is saying is if I have one of these linear transformations, and if it manages to transform each basis vector to 0, so it's basically killing every basis vector, then if it does that, then it actually must kill every vector. Not just the basis vectors, but every vector in the entire vector space. I hinted at this idea earlier today where I sort of said, yeah, if you just tell me what T of a couple of things is, then I can figure out T of everything else. If I tell you where this pixel moves over to here and then this pixel moves over here, I can tell you how the entire screen gets transformed under the function, under that linear transformation. This is kind of the idea. Yeah. Any thoughts about how to start this off? Oscar.
Would you let T equal a certain value?
T is a function, right? So I wouldn't be able to say, this problem is intentionally very abstract. Like we don't know what T is. We don't even know what our vectors are. These could be matrices, they could be polynomials, they could be calculus. We really don't have a solid specific grip on anything. Giovanni?
Just change the equals 0 vector to T vector and I.
So, I'm sorry, one more time?
So instead of, you could swap, since we already established that the 0 T of vector I is equal to 0 vector, you could swap back into the.
So this is telling me that T of V1 is 0, and it's telling me that T of V2 is 0, and so on. All of these are 0. So that's for V1, V2, V3, which is the basis for V. But this vector little v here is not one of these. It's some other arbitrary vector in the vector space. Any thoughts? Bishoy?
The only thing I can think of is that if whatever the function T is, it's gonna be like multiplied by 0 or something like that.
Yeah, I wish we knew what that function T was. They didn't tell us that, unfortunately. It's like very abstract. It's really very abstract. Kim and then Yair. Yeah.
Can you set the V1 and V2 zeros, you multiply together, which is equal to 0, to 0, then it will be in the same universe as V.
So I like you're thinking about it kind of in the right way, except I can't multiply. I heard you say multiply. I can't multiply V1 and V2. That's not allowed, right? But you're on the right track, Zaire, and then sorry, Yair, and then Oscar. Did you have an idea?
I had a question.
Okay, sure.
So W is what we want to get to.
W is the output universe. It's really not playing a very prominent role in what's going on here, though. It's kind of in the background. Yeah.
So you use it on it.
Yeah, we're not going to have to mess around too much with W. Yeah. Oscar?
Could we have the vectors itself be dependent of each other where they equal 0? And then just have the function multiplied by 0?
So these vectors should better not be dependent on each other because they're a basis, right? So there's no dependencies there. But you guys are kind of on the right track. Now I have a confession for you. This was on my exam last time, but I also had a hint. So maybe I'm going to write the hint down because I gave everybody a hint on this, and that I hope will be helpful. So there's a little hint here. And let's see, I was just going to see if we could get it without the hint, but it's kind of tricky. So let me give you the hint. The hint that I wrote on this exam was, how can we write V in terms of the basis? I kind of put it as a question. I said, how could we write the V in terms of the basis? Does that give us any insight? That's it. That's exactly it. You just take this V. Guys, V lives in the universe of the vector space, and everything in the vector space is a linear combination of the basis. Let's do it. Let's start the solution here. That's exactly it. We write V as C1 times V1 plus C2 times V2 plus da 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 plus Cn times Vn. Yeah? Notice that on this first line, I never even mentioned the T. I never even mentioned the transformation at all. It's not even there. I'm just using, this is really from chapter 4, that everything in the vector space is expressible in terms of the basis. Yeah, that's the key idea. It's the power of having a basis. So we can write V like that. And now the question is asking us to figure out T of V. So let's do it. T of V should be T of all of this stuff, C1 V1 plus C2 V2 and dot 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 plus Cn Vn. Right? And we are actually already almost done with the solution. There's not much left to go. So I know we barely learned this even in today a little bit, but if I see T of this linear combination, what is my knee-jerk reaction telling me I'm going to do with that thing?
C1 plus C2 dot 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 is Cn is equal to 0.
Okay, let's go real carefully and slowly. The first term is going to be what?
C1.
C1 times T of V1. Good. And then plus C2 T of V2
plus
That's it. You got it. You got it. You just bust this thing apart. T respects that thing, right? T respects addition and scalar multiplication. So you can totally bust it out like that, yeah? And what is T of V1? 0. What is T of V2? 0. That's what we said already earlier, yeah? So we can just put those things in here. This is C1 times 0 plus C2 times 0 and dot, 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 Cn times 0. I love it. I love it. And you're really just adding up a bunch of zeros. So, of course, that just adds up to 0, which is exactly what we wanted to end up with. Oh, having a linear transformation is so powerful. It allows you to bust out this linear combination because T is going to respect it. T is going to totally respect it.
Did you get this right?
You know, with the hint, so the hint was very helpful, right? The fact that we're going to write our vector as a linear combination. And then, you know, I had trained people up pretty good on this. So on Tuesday, we will be training you up some more on that, this idea of transforming a linear combination by busting it all apart. And so it becomes almost second nature. It's like, even if I don't have any idea what to do, I'm just going to bust it out. Every single time, it's always the right thing to do. Yes, that's right.
So, like the algebra part is never hard. I just like the hardest part for me is like getting that first line.
Getting it set up, yeah.
the big idea.
I totally hear that. Like I'm kind of with you on that, to be honest. Like getting it started is the hardest part. So that's kind of what this is about, right? Sort of saying, okay, and it's not like we've never done this before. Whenever we have a basis, we know that that means that everything in the vector space can be written in terms of that basis. So this should be something that is a theme that, you know, I'm not usually asking questions that you've never seen before the idea, right? So in this case, the importance of what a basis is really at the core of this problem. This is a nice problem that combines chapter 4 with the whole basis concept with this new idea of a linear transformation into sort of one single problem. And I kind of, I don't know, kind of like it actually. Okay, I got a couple more quick things. Is everybody good to hang on for a couple more minutes? Okay, let's just do a couple more things. Back when I was a grad student, I did these review sessions. And I wasn't even the professor, so I wasn't even the one writing the test. But I did these review sessions. I was just a TA, and we would go for hours. I mean, like we would go for like 6 hours. And we'd have to take like dinner breaks and stuff. And I was only like, what, 25 years old or something. Like I could go all night. And I came with like this whole library of problems. And everybody just stayed and stayed and stayed and stayed. I finally just had to say, guys, if I stop doing more problems, will you guys all just go home and get some sleep? And I think we all finally came to an agreement. But it was amazing. Those were marathon sessions. I had to like book out these big auditoriums because I was only teaching like, you know, one of the sections, but then there were all the other TAs with all their students. They heard that I was doing these sessions before the exam, and so then they all wanted to come also. And I had to have this huge room. We just went forever. It was amazing. I was lucky I had a strong voice back then as well, because otherwise I would have needed a microphone. It was so big. So unfortunately, that was like 20 something years ago. I don't have quite the stamina anymore. So I think 3 hours is going to be enough, at least for me for today. Let's just do a couple more things here, guys, and then I'm going to let you go, and I'm going to go get some dinner myself, actually. This is a false statement, and I would like you to tell me why. The span of any two non-zero vectors in R3 must be a plane through the origin. Okay, so the span of any two non-zero vectors in R3 must be a plane through the origin. And like I said, I'm promising you pretty much I'm not going to ask you true, false. If I wanted something like this, I'll tell you it's false. And then what you have to do is figure out why it's false and kind of give me a reason. When something is false, a valid approach would be to actually give an example, if that's what you want to do. You could also just explain it in words. But this is a little more of a visual example. Notice we're working in the universe that you're all familiar with from calculus, R3. And I'm just saying, well, if I took a couple of vectors in R3 and I formed their span, would it have to be a plane through the origin? And it turns out this is not true. Why not? Does anybody think they might have a justification or an example? Kim?
It can be a plane, like outside of origin, like +1, +2, +3.
A plane outside of the origin. Would that be a good reason? Could it be a plane outside of the origin? Okay. Notice that we're talking about the span, right? Anytime I take a span, what do I always have? A subspace. If I have a subspace, what's the first thing I check about the subspace usually? The zero vector. The subspace must have the zero vector, which is the origin. So that justification, Kim, is not going to fly, right? The span of any vectors whatsoever will always include the origin. That's not the thing that's wrong about this. What's the part that's wrong about the statement? Yes, Levi.
that it wouldn't be a plane, it would just be two vectors in 3 dimensions. Well, there'd be three dimensions. Each vector would be 3 dimensions.
Well, a vector is, how many dimensions does a single vector have? Just one, right? And what do you think of when you think of something that's one dimensional?
A line. It is a
line. Is that what you were gonna say?
Well, I was gonna say that it's only it's an R3, meaning dimension 3, and then you only have k equals 2, right?
Okay, that tells me that the span of these vectors would not be the whole R3. It could not span R3. But the real thing I was looking for here, guys, is that it's false because the span of two non-zero vectors could be a line rather than a plane, right? So it could be a line. Let me show you, and I'll actually give you an example. If you just wrote that down, I would give you full credit. But just to give you a really specific example, if I take the span of, let's say, the vector 1, 1, 1, and then I take the vector 2, 2, 2, right? This is only a line, not a plane. So when it said that it had to be a plane through the origin, that was not true. It could be a line through the origin. So you have like 1, 1, 1 is here, yeah. And then 2, 2, 2 is just here. And they're literally on top of each other, pointing in the same direction. So the span of all of that is just a line. Yeah, Eric?
So the statement is true when they're linearly independent?
Yeah, the span of any two non-zero linearly independent vectors would be a plane through the origin. That's a good point. That would have been a good follow-up question. So if I throw in the word linearly independent, if you think about it, two linearly independent vectors have to span 2 dimensions. And 2-dimensional object in R3 would be a plane. Yeah, so that's a good point. Yeah, here these vectors are definitely LD. And so they only give us a line instead of a plane. Does that make sense? Okay, yeah, so there's a little bit of a geometric interpretation there. You want just one more? One more. Okay, I'll give you one more, and then I promise I'm going to stop. But this one, if I do one more, this is the last. These are the 4 theoretical problems I had. It was this one, and then this one, and then that one, and then this one is the last one. And we've done one like this before, so I'm pretty confident you guys are going to nail this one right away. So actually, but I'm going to make it a little harder on you guys. I'm going to ask it as a true false. On the test, I actually told the students whether it was true or whether it was false, but I want to see if you guys can tell me. So if A is 5 by 9, has a nullity of A equal to 4, then is it true or false that the column space of A is equal to R5? Last question for the day. We started this review session talking about null space way back 3 hours ago at the beginning, and now I'm bringing it full circle, and we're going to do one last problem. Oops, one last problem about null space here. Yeah. Well, it's not really about null space, but the null space is related here. True. Think it's true? Okay, let's break it down though, and we'll kind of get to an answer as we go along. When you see this kind of information, what comes into your mind kind of about right at the beginning of it? The rank nullity theorem, exactly. So the rank plus the nullity. I just want to remind everybody, this is very important. I can't imagine this won't be on the test. The rank of A plus the nullity of A has to add up to the number of columns in the matrix, which is the second number up on the top, which is 9. And because they gave us the nullity being 4, that means that the rank of A is 5. Okay, so that's a partial credit right there. If you just wrote that down and stopped, you'd already get probably almost half the points, right? Just for putting this much down. So that's the rank of A. How does the rank of A tell me anything about the column space? Like, what's the connection between the column space and the rank? Oscar.
Well, the rank is the number of pivots, right? So then that means that the call space would have 5 pivots.
Right. The dimension of the column space, which is the number of pivots, is just the rank. So the rank of A, this comes off of that little cheat sheet recap handout. It's definitely a good thing to look at. This tells me that the dimension of the call space of A is equal to 5. So by now you're getting more than half the points on the problem. We're practically almost done. I have a 5-dimensional column space. So that's almost there. That is almost there. The question is, and you guys are right, this is true. It is a 5-dimensional column space. And now I just need to understand, well, why does that mean that it equals R5 specifically? I mean, because again, I mentioned this in class, there's lots of things that are 5-dimensional. Like P4 of R, that's also 5-dimensional, but I wouldn't call that the same thing as R5. They're not the same vector space. Yeah, Eric?
The space is the space of RM. RM is 5, so the dimension equal to the space. So then we could
Okay, somebody was paying attention when we did this in class. Yes, that basically the column space is a subspace of Rm, and in this example, M is 5. So I have a 5-dimensional subspace of R5. That has to be R5 itself. It's a subspace of R5, but it has the same dimension as the whole R5, then it's the whole universe. It's the entire thing. You can't have something that has the same dimension as a big universe within that universe unless it's the entire universe. If that makes sense. I'm kind of talking fast, but
So, I mean, I understand all of that, but like, how would it be a subspace if it's the whole thing?
Well, remember, every vector space is a subspace of itself, kind of in a trivial way.
Yeah.
So it wouldn't be incorrect to call it a subspace of itself. Yeah. So basically, if you wrote all of this down, and you would therefore say, thus, the call space of A is equal to R5. Now, would the row space of A be equal to R5? No, I mean, it would be true that the row space would be 5-dimensional also. The dimension of the row space is also the same as the rank. So the row space is also 5-dimensional, but look at this, guys. The row space is a subspace of R9, so it's not going to be equal to R5. Because R5 is not compatible with R9. They're not even the same universe. So that would be the follow-up question would be, okay, well, is it true that the row space of A is equal to R5? And the answer is no. In fact, the row space is also not equal to R9. Because R9 would have been 9-dimensional and my row space is only 5-dimensional. So they're not even the same size, right? So what is the row space of A? It's not R5. It's not R9. What it is just, you can't really give a good description. All you can say is, oh, it's some 5-dimensional subspace of R9. I have no clue which subspace it is. Right. So, that help a little bit? Kim?
But if 9 is 5, then we be okay.
If this was a 5x5 matrix, yeah, then the row space of A would also be equal to R5. Yeah, that's true. That would be if it was a square matrix, for sure. Yeah.
Kind of going back to what you was talking about, or right there. Would it help to remember that when it's something like that, right, where it's not a square matrix, or it's with the A, M by N, and then kind of like visually see what the dimension is for the closed space or the subspace for the closed space?
Yeah, I mean, I would actually recommend. I mean, I should have done this actually. I think when I did this, there was a homework problem that I did in class like this. It's good to just kind of draw this out and kind of like see it. So you got like 5 dots on each column and 9 dots on each row. It kind of helps you visualize it a little bit. Yeah, you could definitely get some advantage of doing that. Yeah. Well, guys, has this been helpful? Hopefully pretty helpful. Okay, I hope so. I really appreciate you coming today too. I enjoy talking about this stuff. I appreciate your time. Why don't we all go take a break? I'm gonna be in my office later tonight, just kind of getting ready for the week. Probably gonna go hiking tomorrow, but I'll be back to the office by tomorrow night, I think. But during the day tomorrow, I'll probably be out for a little while, just my day off, since I didn't take one today. But I'll just do that, and then I'm gonna be around Monday night, Tuesday, of course, we have class. Wednesday, I'm gonna be around all day. Thursday, we've got the midterm, kind of what the week's looking like. So. All right, I will let you guys go. I'm also gonna send you a extra credit quiz. Does that sound like a good plan? Give you guys some extra points for the midterm if you just work that out. So I'll probably send that out tonight. I'll give you a day or two to finish it. It won't be very long. It'll be something pretty short.